Not all mysteries begin with something hidden. Some begin with something standing in plain sight. A fortress that has dominated a landscape for centuries, a monument visited by thousands of people every year, a ruined city that appears in every history book. These places seem familiar, until archaeologists start asking deeper questions. Suddenly, certainty begins to disappear. Why was it built there and not somewhere else? How did its builders solve problems that should have been impossible for their time? Why do traces of lost knowledge keep appearing around it? The most fascinating ancient mysteries are often not the ones buried underground. They are the ones everyone can see, yet no one can fully explain. Because sometimes the greatest secret of an ancient site is not its existence, but the story that history forgot to preserve. The Mediterranean coast of modern Libya is home to Apollonia, the ancient harbour of Cyrene. More than 2,000 years ago, ships from Greece, Egypt, Carthage and later Rome sailed into this port. Today, much of the harbour lies beneath the sea, creating one of the most fascinating underwater archaeological sites in the Mediterranean. Yet the greatest mystery is not why parts of Apollonia sank. It is how ancient engineers built a harbour so advanced that many of its structures continued functioning for centuries despite earthquakes, storms, and relentless wave attack. Archaeologists first documented the ruins in the 19th century, but the true scale of the harbour only became clear through underwater surveys conducted during the 20th and 21st centuries. Divers discovered submerged quays, breakwaters, warehouses, defensive walls, and enormous stone blocks scattered across the seabed. These remains revealed that Apollonia was not a simple coastal settlement. It was a highly engineered maritime complex that connected one of the wealthiest Greek cities in North Africa to the wider Mediterranean world. The harbour served Cyrene, a city founded by Greek settlers around 631 BC. Cyrene became famous for its agricultural wealth, particularly the valuable plant known as silphium. Trade transformed the region into an economic powerhouse. To support this commerce, Apollonia required a harbour capable of handling large fleets and protecting ships from one of nature's most destructive forces, the sea itself. This leads to the first major mystery. How did ancient engineers choose the exact location of the harbour? Modern port construction begins with extensive geological surveys, wave modelling, and hydrodynamic simulations. Engineers analyse prevailing winds, current patterns, sediment transport, and seabed stability before placing a single structure. The builders of Apollonia possessed none of these technologies. Yet they selected a natural bay that offered remarkable protection while still allowing access to deep water. Satellite imagery and geological studies suggest that the harbour's position took advantage of natural rock formations that reduced wave energy before it reached the inner basin. Whether this was achieved through systematic observation accumulated over generations or through engineering knowledge now lost remains unknown. What is clear is that the location proved successful for centuries. The second mystery concerns construction itself. The harbour contains massive limestone blocks, some weighing several tons. These stones had to be quarried, transported, shaped and positioned with extraordinary precision. Ancient cranes existed in the Greek and Roman worlds, but moving large blocks in a marine environment remains difficult even today. The challenge becomes more impressive when considering the scale of the project. Harbour facilities extended across large sections of the coastline. Hundreds of workers would have been required. Thousands of tons of stone had to be moved, yet no detailed engineering records survive. The logistical achievement invites comparison with other ancient maritime centres. At Caesarea Maritima in modern Israel, Roman engineers created an artificial harbour using hydraulic concrete. At Alexandria in Egypt, massive stone structures protected one of the greatest ports of antiquity. Apollonia belongs in the same category of large-scale coastal engineering, yet receives only a fraction of the attention. The third mystery is perhaps the most remarkable of all. The mystery of the ancient breakwater system begins with a fundamental challenge faced by every successful harbour. Ships require calm water, while the sea rarely provides it. Modern engineers use computer simulations capable of calculating how waves interact with barriers. They model storm surges, seasonal currents, and wave diffraction. Ancient engineers possessed no computers, no mathematical oceanography, and no satellite observations. Yet the harbour of Apollonia incorporated breakwaters positioned with astonishing effectiveness. Archaeological surveys indicate that protective structures were placed in locations that reduced incoming wave energy before it entered the harbour basin. The arrangement appears simple at first glance. In reality, designing such a system requires understanding how waves bend, reflect, and dissipate energy. How did ancient builders determine the optimal placement? One possibility is centuries of accumulated maritime experience. Sailors, fishermen, and harbour builders may have observed wave behaviour over generations. Another possibility is that practical engineering traditions existed that were never written down and disappeared after antiquity. The effectiveness of the system becomes even more impressive when compared with modern coastal engineering principles. Contemporary breakwaters often aim to reduce wave heights by 50 to 90% depending on conditions. While precise measurements for Apollonia are impossible, the harbour's long operational history suggests that its defences performed exceptionally well. Researchers studying ancient ports have noted that successful harbour design often reflects a sophisticated understanding of local environmental conditions. At Apollonia, the breakwaters appear carefully integrated into the natural coastline rather than imposed upon it. This strategy resembles modern, sustainable coastal engineering, which increasingly seeks to work with natural geography rather than against it. The fourth mystery involves the submerged sections of the harbour. Today, significant portions of Apollonia lie beneath several metres of water. Stone quays, walls, and harbour installations are visible on the seabed. Geological evidence suggests that a combination of tectonic activity and sea level change contributed to this transformation. Historical records indicate that the region experienced major earthquakes during late antiquity. The earthquake of AD 365, one of the most powerful known Mediterranean earthquakes, generated a massive tsunami and caused widespread destruction from Greece to North Africa. Some researchers believe that events of this magnitude may have contributed to the harbour's gradual submergence. Yet many questions remain unresolved. Did the harbour sink suddenly during catastrophic earthquakes, or did it slowly descend over centuries through geological processes? The answer has important implications for understanding ancient coastal landscapes throughout the Mediterranean. The fifth mystery concerns material durability. Marine environments are among the most destructive settings for architecture. Saltwater accelerates erosion. Waves create constant mechanical stress. Biological organisms attack stone surfaces. Modern coastal infrastructure often requires extensive maintenance. Yet parts of Apollonia survived for more than 2 millennia. This durability suggests that ancient builders possessed a deep understanding of material selection. Limestone from local quarries appears to have been chosen carefully. Construction techniques may have minimized structural weaknesses. Some researchers have even suggested that certain mortars used in Mediterranean coastal architecture possessed properties that enhance long-term durability. The comparison with Roman maritime concrete is unavoidable. scientists studying Roman harbour structures have discovered mineral formations that continue strengthening concrete after centuries of exposure to seawater. Although Apollonia was not built entirely with Roman concrete, its survival raises similar questions about lost material knowledge. The sixth mystery involves navigation. Apollonia functioned as a gateway connecting North Africa with the wider Mediterranean. Ships arriving from Greece, Egypt, Sicily and the Levant depended upon accurate navigation and reliable harbour facilities. Without modern lighthouses, GPS systems, radar or electronic charts, mariners still managed to conduct regular long-distance voyages across hundreds of kilometres of open water. Ancient sailors relied upon stars, coastal landmarks, seasonal winds, and accumulated experience. Yet the consistency of Mediterranean trade suggests a level of navigational expertise far greater than many people imagine. The harbour itself likely played a role in this system. Its design may have incorporated visual markers, defensive towers, and entrance alignments that guided vessels towards safe anchorage. What do you think was the secret behind Apollonia's remarkable harbour engineering? Share your thoughts in the comments below. Kazanlak, central Bulgaria. Beneath a modest earthen mound lies a small circular tomb that contains some of the most astonishing paintings ever created in the ancient world. More than 2,300 years after they were painted, their colours remain visible, their details remain sharp, and the technology behind them remains only partially understood. The Thracian tomb of Kazanlak is often described as an archaeological treasure. In reality, it may be one of the greatest technological mysteries of ancient Europe. The tomb was discovered accidentally in 1944 when soldiers digging defensive positions near the city of Kazanlak broke into an underground chamber. What they found stunned archaeologists. Inside was an almost perfectly preserved Thracian burial monument dating to the late 4th or early 3rd century BC, decorated with extraordinary murals unlike anything previously known from Thracian civilization. Today the tomb is recognized as a UNESCO World Heritage Site, yet many of its engineering secrets remain unresolved. The first mystery appears before anyone even studies the paintings. The burial chamber consists of a narrow corridor leading into a circular domed room approximately 2.65 meters in diameter. The dome itself was constructed from carefully arranged bricks that create a nearly perfect geometric structure. This may not sound extraordinary until one considers the period. The tomb was built more than 2 centuries before the Roman Empire reached its architectural peak. There were no laser levels, no precision surveying instruments, no modern engineering calculations, and no steel reinforcement. Yet the dome has survived over 23 centuries despite earthquakes, seasonal temperature fluctuations, soil pressure, and moisture exposure. Modern engineers studying ancient masonry structures often note that even minor geometric errors can significantly weaken a dome. The remarkable symmetry of Kazanlak suggests that Thracian builders possessed surveying techniques far more sophisticated than traditionally assumed. How did they establish such accuracy underground? No surviving manuals provide an answer. The second mystery involves the materials themselves. The paintings were not applied directly onto raw brick surfaces. Builders first created carefully prepared plaster layers designed to receive pigments. For over 2,300 years, these surfaces have resisted cracking, separation, and deterioration. Modern conservation studies indicate that the plaster contains highly refined lime mixtures combined with carefully selected aggregates. The quality of preparation appears unusually high for the period. The challenge is that ancient lime technology was far from simple. Producing durable plaster requires precise control of firing temperatures, slaking procedures, mixing ratios, curing conditions, and application timing. Small mistakes can dramatically reduce long-term stability. Yet the Kazan-Lak surfaces continue to support paintings that have survived longer than many medieval artworks. Researchers still debate whether organic additives, plant extracts, proteins, or other stabilizing materials may have been incorporated into the mixture. The complete recipe remains unknown. The greatest mystery of Kazan-Lak is undoubtedly its artwork. The circular chamber contains scenes depicting a Thracian nobleman and his wife participating in a ceremonial banquet. Around them are servants, musicians, horses, chariots, and ritual figures. Above them, the curved dome becomes a continuous narrative painted with astonishing precision. At first glance, the paintings appear merely beautiful. Closer examination reveals something far more remarkable. They survived. Many ancient murals have vanished entirely. Others survive only as fragments. Even masterpieces from later periods often suffer severe fading, pigment loss, salt damage, biological growth, or surface detachment. The Kazan-Lak paintings remain visible after more than 23 centuries. This raises a fundamental technological question. How? Scientific analysis has identified pigments based largely on naturally occurring minerals. Red tones appear linked to iron oxides. Black pigments likely derive from carbon-based materials. White areas were created using lime-rich compounds. These materials were known throughout the ancient Mediterranean. What remains difficult to explain is the extraordinary stability achieved by the Thracian painters. Modern microscopic examinations suggest that pigments were applied through carefully controlled processes, rather than simple decorative painting. Some areas reveal multiple layers, indicating a sophisticated understanding of colour preparation and surface interaction. Researchers have compared aspects of the technique with fresco traditions later perfected in Roman and Renaissance art. The comparison is surprising because the Kazan-Lak murals predate many of the most famous surviving fresco cycles by centuries. Even more impressive is the artist's mastery of visual effects. Human faces display subtle emotional expressions. Horses appear dynamic and energetic. Clothing folds create convincing depth. Shading techniques generate three-dimensional illusions on curved surfaces. These achievements required more than artistic talent. They required technical knowledge. The painters understood how pigments behaved on wet plaster, how colours changed during drying, how mineral particles interacted with binders, and how environmental conditions affected long-term durability. Such knowledge could only have emerged through generations of experimentation. Yet almost none of that knowledge was written down. One of the most puzzling scientific questions concerns pigment preservation. Exposure to humidity, oxygen, microorganisms, and chemical reactions normally causes gradual degradation. In many ancient sites, colours disappear entirely after only a fraction of Kazan-Lak's lifespan, yet numerous pigments remain identifiable today. Some conservation scientists suspect that the microenvironment inside the tomb played a critical role. Others emphasize the exceptional quality of the plaster. Still others point toward the purity of the mineral pigments themselves. The truth may involve all three factors. What makes the puzzle particularly fascinating is that modern laboratories can identify the surviving materials, but reconstructing the exact ancient manufacturing process remains far more difficult. The final product survives, the production knowledge does not. Another technological puzzle involves preservation conditions. Underground structures typically face constant threats from groundwater, humidity fluctuations, fungal growth, and temperature changes. Yet the tomb protected its paintings for more than 23 centuries. This suggests that the builders may have understood local geology and drainage conditions at a surprisingly advanced level. The burial mound itself likely acted as a natural environmental buffer. Temperature changes underground occur far more slowly than at the surface. Moisture movement can also be influenced by careful site selection and construction techniques. Modern climate-controlled museums achieve similar objectives using sensors, ventilation systems, and computer monitoring. The Thracians achieved remarkable preservation without any of these technologies. Perhaps the greatest mystery is not the tomb itself, it is the disappearance of the knowledge behind it. The builders understood geometry, structural engineering, material science, and environmental control. The painters understood pigments, chemistry, optical effects, and preservation techniques. The craftsmen understood how to transform ordinary minerals into colours capable of surviving for millennia. Yet almost none of their technical explanations remain. What do you think was the greatest secret behind Kazanlak's remarkable preservation? The pigments, the plaster, or the engineering itself? Share your thoughts in the comments below. In southern Tajikistan, near the banks of the Vakhsh River, archaeologists uncovered the remains of a royal city that flourished more than 1,000 years ago. Beneath layers of earth lay the forgotten capital of the medieval kingdom of Kutal, a centre of power that reached its height between the 9th and 11th centuries AD. What researchers expected to find was another ruined fortress. What they discovered instead was evidence of sophisticated engineering, advanced water management, remarkable architectural planning, and one of the most mysterious plaster technologies ever identified in Central Asia. More than 1,000 years later, many of its secrets remain unsolved. The ruins of Hulbuk were identified through archaeological investigations conducted during the 20th century. Excavations gradually revealed the remains of a vast palace complex covering several hectares, decorated with elaborate carved plaster, monumental halls, courtyards, and hydraulic infrastructure. The discoveries transformed Hulbuk from a forgotten name in medieval chronicles into one of the most important archaeological sites in Central Asia. Yet the deeper researchers looked, the more mysteries emerged. The first mystery concerns scale. Hulbuk was not a simple fortress. Excavations revealed a large administrative and residential complex that once served as the political heart of an entire kingdom. The palace contained multiple courtyards, ceremonial halls, private chambers, service areas, and defensive structures arranged according to a carefully organised plan. Creating such a complex required accurate surveying techniques. Even today, construction projects depend upon measurement systems capable of maintaining geometric consistency across large distances. Medieval builders lacked laser levels, satellite positioning, and modern engineering software. Yet many sections of Hulbuk display remarkable symmetry. Researchers continue to debate how medieval surveyors achieved such precision using only simple tools. The challenge becomes even greater when considering the region's seismic activity. Tajikistan lies within one of the most tectonically active zones in Central Asia, where earthquakes have repeatedly reshaped the landscape. Despite this, substantial portions of the palace foundations survived for centuries. How did the builders design structures capable of enduring such conditions? The answer remains uncertain. Among all of Hulbuk's engineering puzzles, none may be more fascinating than its decorative plaster. Archaeologists uncovered walls covered with intricate stucco ornamentation, geometric patterns, floral motifs, and highly detailed relief carvings. At first glance, these decorations appear artistic. Upon closer examination, they reveal a remarkable technological achievement. Many surviving details measure only a few millimeters in width, and some edges remain surprisingly sharp despite exposure to more than a millennium of environmental stress. Creating such precision required far more than artistic skill. It required materials science. Traditional gypsum plaster is produced by heating gypsum stone to temperatures generally ranging between approximately 120 and 180 degrees Celsius. The resulting material must then be carefully mixed with water in precise proportions. Even slight variations in composition can significantly alter strength, workability, drying behavior, and durability. The mystery is that Hulbuk's craftsmen consistently achieved exceptional results. Researchers analysing fragments have found evidence suggesting carefully controlled production methods. The plaster exhibits characteristics that indicate an advanced understanding of raw materials and manufacturing processes. Yet no written technical manuals survive. No recipes have been discovered. No workshop records explain how the material was produced. The situation resembles one of history's most famous technological mysteries, Roman concrete. For decades, scientists studied Roman harbour structures that survived nearly 2,000 years of exposure to seawater. Modern analysis revealed unusual mineral formations created through complex chemical interactions between volcanic ash, lime, and seawater. The builders clearly understood processes that were never fully documented. Hulbuk presents a similar puzzle. The decorative plaster demonstrates expertise, but the knowledge behind it has largely vanished. Another mystery involves production consistency. Thousands of decorative fragments have been recovered from the site. Maintaining uniform quality across such large quantities would have required standardized manufacturing procedures. This implies specialized workshops, trained artisans, quality control systems, and reliable sources of raw materials. Yet the industrial infrastructure that supported this production remains poorly understood. How were materials transported? How were craftsmen trained? How were production standards maintained over generations? Archaeology has yet to provide complete answers. Some researchers suspect that medieval Central Asian craftsmen possessed highly refined practical knowledge accumulated through centuries of experimentation. If true, Hulbuk may preserve evidence of a lost technological tradition whose details disappeared long ago. A palace cannot function without water. This fact creates another puzzle. Southern Tajikistan experiences periods of significant seasonal dryness. Sustaining a major urban centre required dependable access to water for drinking, sanitation, agriculture, and daily life. Excavations have identified channels, drainage systems, and evidence of hydraulic planning. These discoveries suggest a sophisticated approach to water management. Ancient engineers appear to have understood how to control gradients, direct flow, and prevent structural damage caused by water accumulation. The challenge is that much of the original system remains buried or destroyed. Researchers can see fragments of the network, but not the entire design. This situation mirrors ancient Qanat systems across Persia, where underground tunnels transported water over vast distances while minimizing evaporation. Did Hulbuk employ similar principles? The evidence is intriguing but incomplete. Perhaps the most surprising mystery is structural durability. Central Asia experiences frequent seismic activity. Throughout history, earthquakes have destroyed cities, altered rivers, and damaged countless monuments. Yet portions of Hulbuk endured. Excavated foundations reveal thick walls and construction methods that may have helped distribute stress. Some sections appear to combine different building materials, potentially improving structural flexibility. Modern engineers understand that mixed materials can sometimes dissipate energy more effectively than rigid monolithic structures. Whether medieval builders intentionally applied such principles remains unknown. The question raises a fascinating possibility. Did generations of builders develop practical earthquake-resistant techniques through observation and experience? Or was their success merely accidental? Researchers continue to investigate. The artifacts discovered at Hulbuk reveal connections extending far beyond the kingdom itself. Excavations have produced imported ceramics, luxury goods, glassware, metal objects, and decorative materials originating from distant regions. These finds indicate participation in extensive trade networks linked to the Silk Road. Maintaining such connections required organisation on a remarkable scale. Merchants, craftsmen, administrators, and transport systems all contributed to the city's prosperity. Yet many aspects of this economic system remain poorly understood. The palace itself suggests access to considerable wealth. Exactly how the wealth was generated remains a matter of ongoing research. What do you think was Hulbuk's greatest lost technology? The extraordinary plaster, the hidden water system, or something we have not yet discovered? Share your thoughts in the comments below. In a quiet field near the village of Rogozan in northwestern Bulgaria, archaeologists uncovered something extraordinary. Buried beneath the soil was the largest Thracian silver treasure ever discovered. 165 silver vessels weighing more than 20 kilograms. The discovery was accidental. In 1985, a local farmer digging an irrigation trench struck several metal objects. Archaeologists were called in and soon uncovered one of the most remarkable treasure hoards in European history. What they found was not merely a collection of valuable artifacts, it was evidence of a technological system whose sophistication continues to puzzle researchers today. The greatest mystery is not the treasure itself. The greatest mystery is how the Thracians managed to produce it. The first and perhaps most important mystery concerns silver production itself. At first glance, silver vessels may seem simple compared to pyramids or fortresses. In reality, silver production was one of the most technologically demanding industries of the ancient world. Most silver in antiquity was extracted from lead-rich ores such as galena. Producing usable silver required multiple stages of mining, crushing, smelting, refining, and purification. The most critical process was cupellation. Cupellation separates silver from the lead by heating the metal mixture to temperatures approaching 900 to 1000 degrees Celsius, while maintaining carefully controlled airflow. Under these conditions, lead oxidizes and is removed, leaving silver behind. Even small mistakes can ruin the process. Too little oxygen prevents separation, too much heat can damage the metal, and poor furnace design reduces efficiency. Yet the Rogozan vessels demonstrate access to large quantities of refined silver over a period spanning nearly 2 centuries. This creates a major archaeological problem. Where were the production centres? The treasure contains enough silver to imply a large-scale mining and refining operations, but relatively few associated industrial sites have been identified. Researchers know that ancient silver mines existed throughout the Balkans, including regions associated with Thracian tribes. However, the scale of production implied by the Rogozan treasure suggests a far more extensive metallurgical network than currently documented. Some scholars compare this mystery to the Roman concrete puzzle. Modern researchers can analyze the final product, but reconstructing the complete production system remains difficult. The Thracians left silver, but they did not leave engineering manuals. The challenge becomes even more remarkable when one considers fuel requirements. Ancient silver production consumed enormous quantities of charcoal. Producing 1 kilogram of refined silver could require processing vast amounts of ore and burning substantial quantities of fuel. Maintaining temperatures near 1000 degrees Celsius demanded expert knowledge of furnace geometry, airflow dynamics, fuel quality, and ore composition. They achieved this without thermometers, without modern chemistry, and without written technical instructions. Yet somehow they succeeded. The treasure contains 165 vessels created across different periods. Despite this, many display remarkable consistency in workmanship. Wall thicknesses remain surprisingly uniform, decorative styles show continuity, and manufacturing quality remains exceptionally high. Such consistency raises important questions. How was technical knowledge transmitted? Did specialized workshops exist? Were apprentices trained according to standardized methods? Or did elite craftsmen travel between royal courts sharing techniques across the Thracian world? This level of continuity suggests something more sophisticated than isolated artisans working independently. It suggests an organized technological tradition. Many vessels contain incredibly detailed decorative scenes featuring animals, mythological creatures, human figures, and complex geometric patterns. Some details are only a few millimeters wide, making their execution all the more impressive. Creating such artwork on curved silver surfaces is extraordinarily difficult. The craftsmen used techniques known today as repousse and chasing. Repousse involves hammering metal from the reverse side to create raised forms, while chasing refines those forms from the front. Modern metalworkers understand how challenging this process can be. Every strike affects the shape of the entire surface. Too much force creates cracks, while too little force produces weak details. The precision achieved by the Rogozan artisans remains remarkable even by modern standards. Several vessels contain traces of gilding. This means ancient craftsmen successfully bonded gold to silver surfaces. The process required more than artistic skill, it required practical chemistry. The metal surface had to be prepared carefully, contamination had to be minimized, and bonding techniques had to ensure durability. Some gilded areas survived more than 2,000 years underground. This durability continues to attract scientific attention. Researchers still debate exactly which gilding techniques were used and how knowledge of these methods spread throughout the ancient Balkans. The treasure reveals influences from multiple cultures. Certain decorative motifs resemble Greek art, others show characteristics associated with Persian traditions, and some elements appear distinctly Thracian. This combination suggests extensive technological exchange across enormous distances. The ancient Balkans were not isolated. Instead, they may have functioned as part of a vast network connecting Europe, Anatolia, the Black Sea region, and the Near East. Ideas travelled, materials travelled, and artisans may have travelled as well. The Rogozan treasure provides evidence that technological globalization existed long before the modern world. More than 100 vessels bear inscriptions. Many contain names of Thracian rulers, while others may indicate ownership, political alliances, or ceremonial functions. These inscriptions offer a rare glimpse into Thracian society, yet many questions remain. Were these marks inventory records, royal property labels, workshop signatures, or religious symbols? No consensus exists. The inscriptions may represent one of the earliest surviving systems for tracking valuable metal assets in the region. Perhaps the most obvious mystery remains unanswered. Why was the treasure hidden? The vessels represented enormous wealth. Their artistic value was immense, and their political significance may have been even greater. Several theories have been proposed. The treasure may have been concealed during warfare. It may have served as a ritual offering. It may have belonged to a royal treasury hidden during a political crisis. Or it may have formed part of a sacred deposit never intended to be recovered. No theory fully explains the evidence. The identity of the person who buried the treasure remains unknown. The final mystery may be the most important. The vessels, silver, and inscriptions survived, but much of the knowledge behind them did not. No surviving texts explain Thracian furnace design, silver refining, or mining techniques. Modern tools such as isotopic analysis, electron microscopy, and 3D scanning reveal remarkable details, yet they cannot fully recover centuries of practical expertise. The Rogerson treasure reminds us that ancient technology was often more advanced than surviving records suggest. The silver remains, but the craftsmen who created these masterpieces are gone, and that may be the greatest mystery of all. Located on a strategic hill west of Dushanbe, Tajikistan, the Hisor fortress has witnessed the rise and fall of empires for more than 2,000 years. Yet one mystery remains. How did ancient builders create a fortress capable of surviving centuries of warfare, earthquakes, and extreme climate using technologies that are still not fully understood today? The fortress has been known locally for centuries, but systematic archaeological investigations during the 20th century reveal that the visible structures represent only the latest phase of a much older occupation. Excavations uncovered evidence of settlements, fortifications, workshops, and infrastructure spanning multiple civilizations, suggesting that Hisor was not merely a fortress, but a long-term center of engineering, administration, and regional control. The first mystery begins with geography. Hisor occupies one of the most strategically advantageous positions in Central Asia. The fortress overlooks the fertile Hisor Valley while controlling routes that connected ancient Bactria, Persia, and later sections of the Silk Road network. Modern military analysts often evaluate defensive sites using factors such as visibility, access to resources, transportation corridors, and natural barriers. Remarkably, Hisor satisfies nearly all of these requirements. From the fortress, defenders could monitor movement across vast sections of the valley, while nearby agricultural land could support large populations. Water sources were accessible, and mountain ranges provided additional protection. The mystery is not that the fortress was built here. The mystery is how ancient surveyors identified such an optimal location without aerial mapping, satellite imagery, or modern geographic analysis. Recent digital elevation models show that the fortress commands one of the most advantageous viewpoints in the region, suggesting a sophisticated understanding of terrain analysis long before modern cartography existed. At first glance, Hisor appears to be a simple hilltop fortress. Archaeological evidence suggests otherwise. Researchers believe the visible walls formed only one component of a larger defensive network that may have included observation posts, outer fortifications, controlled access routes, and supporting military infrastructure. Ancient military engineers understood a principle still used in modern warfare: defense in depth. Rather than relying on a single wall, effective fortifications force attackers through multiple defensive zones, with every additional obstacle increasing casualties and slowing an assault. This principle can be observed in Roman frontier forts, Byzantine strongholds, and medieval castles throughout Eurasia. The question is whether the builders of Hisor independently developed similar concepts or inherited military engineering traditions that have since disappeared from the historical record. Because many earlier structures were rebuilt or destroyed over centuries, archaeologists still cannot reconstruct the fortress's original defensive layout with complete confidence. Among all engineering puzzles at Hisor, none may be more fascinating than its construction materials. The fortress exists in an environment that should be extremely hostile to earthen architecture. Temperatures can vary dramatically between seasons, while rainfall, freeze-thaw cycles, erosion and seismic activity continuously attack exposed structures. Under such conditions, many mud brick buildings deteriorate within decades if not maintained. Yet portions of Hisor survived for centuries. How? The answer may lie in a sophisticated material technology that remains only partially understood. Many ancient Central Asian builders relied on combinations of fired brick, mud brick, and rammed earth. To modern observers, these materials may appear simple, but in reality they represent highly complex engineering systems. Rammed earth is created by compressing successive layers of soil inside wooden forms, a process capable of producing structures with remarkable strength. Modern tests on historical rammed earth walls have demonstrated compressive strengths ranging from approximately 1 to several megapascals depending on composition and construction quality. The mystery is that ancient builders achieved consistent results without laboratories, material testing equipment, or engineering textbooks. Excavations throughout Central Asia suggest that builders carefully selected soils based on particle size distribution. Clay provided cohesion, sand reduced shrinkage, gravel improved structural stability, and organic fibres could reduce cracking. Some mixtures may have included ash or mineral additives. At Hizor, researchers suspect similar techniques were employed, but the precise recipes remain unknown. This problem resembles one of archaeology's most famous material mysteries, Roman concrete. For decades, scientists wondered why Roman harbour structures survived nearly 2,000 years of exposure to seawater. Recent studies revealed unusual mineral growth inside the concrete that actually strengthened the material over time. Hizor may represent a similar case. Ancient builders may have discovered optimal soil compositions through centuries of experimentation. Their knowledge was likely transmitted orally from master builders to apprentices, and when these traditions disappeared, the technical knowledge vanished with them. Even more intriguing is the possibility that different layers of the fortress employed different material formulas depending on structural requirements. Some sections may have prioritized strength, others flexibility, and still others may have been designed specifically to resist seismic vibrations. Without complete chemical and microstructural analysis of every surviving section, the full engineering logic remains hidden. Hizor lies within a region affected by significant seismic activity. Throughout Central Asia, earthquakes have repeatedly destroyed cities and monuments, yet parts of the fortress endured. This raises another engineering mystery. Modern earthquake-resistant structures rely on principles such as energy dissipation, load distribution, flexibility, and controlled deformation. Many ancient fortifications unintentionally incorporated similar characteristics. Thick walls possess enormous mass. Rammed earth cores can absorb vibration, broad foundations distribute loads, and relatively low structures reduce collapse risk. Researchers studying ancient earthquake-resistant architecture have noted comparable features in sites ranging from Machu Picchu in Peru to certain Persian and Central Asian fortifications. Were the builders of Hizor consciously designing for earthquakes, or were they gradually refining construction methods after generations of observing structural failures? No written records provide a definitive answer. A fortress cannot survive without water. This simple fact creates another mystery. Hizor supported soldiers, administrators, craftsmen, merchants, and local populations over long periods. Such communities required reliable water supplies throughout both peace and conflict. Evidence suggests the existence of sophisticated water management systems involving channels, reservoirs, and distribution networks. The challenge becomes even more impressive when considering the climate of Central Asia. Water availability fluctuates seasonally, droughts occur, and military sieges can disrupt access. To maintain a functioning fortress under such conditions required careful planning. Ancient Persian qanat systems transported groundwater across deserts for dozens of kilometers, while Roman aqueducts delivered millions of liters daily to major cities. The question is whether Hizor employed similarly sophisticated hydraulic solutions that remain undiscovered beneath later construction layers. Hizor was never isolated. It formed part of a broader landscape of settlements, watchpoints, and trade routes. Researchers suspect that visual communication systems may once have linked elevated positions throughout the region. Fire beacons, smoke signals, reflective surfaces, and observation towers have been documented in numerous ancient civilizations. The Great Wall of China used beacon towers capable of transmitting warnings across hundreds of kilometers in remarkably short periods. Could a smaller but similar network have existed around Mysore? The geography certainly suggests the possibility, yet direct evidence remains frustratingly scarce. What do you think was the greatest engineering secret of his or fortress? The strategic location, the earthquake-resistant design, or the mysterious fired brick and rammed earth technology? Share your thoughts in the comments below. Starocell is one of the most astonishing engineering mysteries of the ancient world. Hidden among the hills of central Bulgaria, about 140 kilometers east of Sofia, this massive Thracian temple complex has survived for more than 2,300 years. Built during the 4th century BC, possibly under the rule of the powerful Thracian king Soothes III, the site contains some of the largest ritual structures ever created by the Thracians. What makes Starocell extraordinary is not merely its age, but the level of engineering knowledge preserved in stone. Massive blocks weighing several tons were transported across difficult terrain. A circular sacred enclosure more than 240 meters in diameter was constructed with remarkable precision. And most astonishing of all, the builders created a gigantic stone dome that continues to stand after centuries of earthquakes, weathering, and human activity. The temple raises a question that archaeologists still cannot fully answer. How did a civilization often described as tribal achieve engineering results that rivaled some of the most sophisticated stone builders of the ancient Mediterranean? Although local people had known about the mound for centuries, the true importance of Starocell was revealed only in the year 2000, when archaeological excavations led by Georgi Kitov uncovered a monumental Thracian cult complex hidden beneath the landscape. What emerged was one of the largest and most elaborate Thracian religious sites ever discovered, and with every new excavation came new mysteries. The first mystery begins long before construction. The temple contains enormous granite blocks, some weighing several tons. Transporting such material today would require heavy machinery, yet the builders of Starocell had no engines, cranes, steel cables, or modern vehicles. Researchers believe the stone may have been transported from quarries located kilometers away. Even a relatively modest 5-ton block presents a significant logistical challenge. Experimental archaeology has shown that moving such weights using only wooden sledges and human labour requires careful route preparation, precise coordination, and large work crews. The challenge becomes even greater when considering elevation changes. The terrain surrounding Starocell is far from flat, and every additional degree of slope dramatically increases the force required to move heavy loads. The builders clearly possessed a sophisticated understanding of logistics, yet no written records explain how the operation was organised. Like the builders of Stonehenge, they left behind the result but not the instructions. The greatest engineering puzzle at Starocell lies inside the temple itself. At the centre of the complex stands a monumental chamber covered by a massive stone dome constructed using carefully arranged stone courses. More than 2 millennia later, much of the structure remains intact. At first glance, the dome appears simple. In reality, it represents one of the most difficult architectural challenges in the ancient world. A stone dome is fundamentally unstable during construction because every block exerts force not only downward, but also outward. If those forces are not perfectly balanced, collapse becomes inevitable. Modern engineers solve this problem using mathematical calculations, structural modelling software, reinforced concrete, and steel support systems. The Thracians had none of these tools yet somehow they succeeded. The dome was built using a corbelled technique in which each successive ring of stones projects slightly inward relative to the layer below. Over time, the opening narrows until it can be closed at the top. The principle sounds straightforward, but the execution is extraordinarily difficult. Each stone must be positioned with remarkable precision. If the inward projection is too large, instability increases. If it is too small, the dome cannot close properly. Small cumulative errors become catastrophic as height increases. Engineers studying ancient corbelled structures have demonstrated that deviations of only a few centimetres can dramatically alter stress distribution throughout the structure. What makes Starocell remarkable is that the builders achieved this precision without laser measurements, modern surveying instruments, or structural calculations. Even more intriguing is the durability of the design. Bulgaria lies within a region influenced by seismic activity from the Balkan and Anatolian tectonic systems, and throughout the last 2,000 years numerous earthquakes have affected the region. Yet the dome endured. Why? One possibility is that the builders understood structural behaviour through generations of accumulated practical experience. They may not have possessed mathematical formulas, but they understood which proportions worked and which failed. Another possibility is that the design itself contains geometric relationships that naturally distribute stress efficiently. This phenomenon appears elsewhere in the ancient world. The treasury of Atreus in Greece, constructed around 1250 BC, contains a corbelled dome nearly 14.5 metres high that remains standing today. The builders of Newgrange in Ireland created a similar structural solution more than 5,000 years ago. In Peru, Inca stonework demonstrated extraordinary resistance to seismic forces despite the absence of mortar. Starocell belongs in this same category of ancient engineering achievements that appear deceptively simple but conceal sophisticated structural knowledge. The mystery is not that the dome exists, the mystery is that it still exists. Surrounding the temple is a massive circular wall measuring approximately 240 metres in diameter. Creating such a circle sounds easy on paper, but it is not. Maintaining geometric consistency across hundreds of metres requires accurate surveying methods, and even minor measurement errors become increasingly visible as the circle expands. Modern surveyors use total stations, GPS equipment, and digital mapping software. The Thracians relied on ropes, stakes, and human observation. Yet the enclosure displays a level of planning that suggests considerable geometric knowledge. How this knowledge was acquired remains uncertain. Several researchers have suggested that elements of the temple may have been aligned with significant solar events. Ancient civilizations frequently integrated astronomy into religious architecture. The Great Pyramid of Giza exhibits remarkable cardinal orientation. Newgrange is aligned with the winter solstice sunrise, and Chichen Itza creates famous shadow effects during equinoxes. Starocell may represent a Thracian version of the same phenomenon. If true, the builders were not merely architects, they were also observers of the sky. The extent of this knowledge remains debated. Which Starocell mystery fascinates you the most? The massive stone dome, the astronomical alignments, or the lost engineering knowledge behind it all? Let us know your thoughts in the comments below. A giant burial mound in central Bulgaria concealed one of the greatest technological mysteries of the ancient world. Beneath its stones lay the tomb of a Thracian king, an engineering masterpiece over 2,300 years old, and a bronze head so sophisticated that some experts consider it among the finest surviving portraits from antiquity. The location is Golyama Kusmatka, near modern Kazan-Lak in Bulgaria's famous Valley of the Thracian Kings. The discovery came in 2004 when Bulgarian archaeologist Georgi Kitov excavated the mound and uncovered a remarkably preserved royal tomb believed to belong to Suths III, ruler of the powerful Odrysian kingdom during the late 4th century BC. What emerged from the earth was not merely a royal burial. It was a collection of technological mysteries that continue to puzzle archaeologists, engineers, metallurgists, and historians today. The first mystery begins with the tomb itself. The structure consists of a long entrance corridor, a rectangular antechamber, a circular domed chamber, and an inner burial room. Massive stone blocks weighing several tons were cut, transported, and assembled with remarkable precision. Many joints remain extraordinarily tight even after more than 23 centuries. Modern engineers understand how such construction can be achieved using advanced surveying equipment and mathematical calculations. What remains unclear is how Thracian builders achieved similar precision using Iron Age technology. The circular chamber is particularly intriguing. Its dome resembles the Tholos tombs of Mycenaean Greece, structures that required sophisticated understanding of load distribution and structural stability. Every stone had to be positioned carefully so the weight of the entire dome would compress inward rather than collapse outward. A minor error could have destroyed the entire structure, yet the chamber has survived earthquakes, centuries of weathering, and the enormous pressure of the burial mound above it. Researchers still debate whether Thracian builders independently developed this knowledge, adapted it from Greek influences, or inherited engineering traditions whose origins have been lost. The second mystery involves transportation. The tomb required enormous quantities of stone. Some blocks weigh several tons and were moved across difficult terrain without cranes, trucks, steel cables, or modern machinery. Experimental archaeologists studying ancient construction have repeatedly demonstrated that moving heavy stone is possible using ropes, wooden sledges, rollers, and coordinated labour. However, possibility does not automatically explain reality. The exact logistics used by the builders remain unknown. How many workers participated? How were slopes negotiated? How were stones lifted into precise positions? No surviving documents provide answers. The third mystery concerns the remarkable durability of the structure. Bulgaria lies within a region that has experienced significant seismic activity throughout history. Many ancient buildings have suffered severe structural damage, yet major sections of the tomb remain astonishingly stable. Some structural engineers suggest that the circular geometry of the chamber naturally distributes seismic forces more effectively than rectangular designs. Others point to the massive wall thickness and careful stone placement. Whatever the explanation, the builders appear to have achieved a level of long-term structural resilience that continues to impress modern specialists. The fourth mystery centres on the tomb's ceremonial ceiling. After Suths III was buried, the entrance was intentionally blocked. Large stones were positioned to prevent access. The burial mound itself became part of the monument. Archaeologists discovered evidence suggesting that specific ritual actions occurred before the final closure. Objects were carefully arranged. Weapons were placed deliberately. Symbolic items occupied precise locations. The exact meaning of these actions remains uncertain. But the greatest mystery of all was waiting near the entrance. There, archaeologists discovered a bronze head. Not a complete statue, only the head, and that changes everything. The bronze head of Suths III is widely considered one of the greatest masterpieces of ancient portrait sculpture ever discovered. At first glance, it appears almost modern. The facial proportions are astonishingly realistic. The eyes convey psychological depth. Individual features display subtle asymmetries typical of real human faces. the expression possesses a level of individuality rarely seen in ancient sculpture. For historians of art, it is extraordinary. For metallurgists, it is even more extraordinary. Creating such an object required one of the most advanced manufacturing technologies of the ancient world, lost wax casting. This process begins with a detailed wax model. The model is covered with clay, the wax is melted away, molten bronze is then poured into the resulting cavity. The technique sounds simple. In reality, it is extremely difficult. The furnace must reach temperatures exceeding 1000 degrees Celsius. The alloy composition must be carefully controlled. The mould must withstand thermal stress without cracking. The molten metal must flow evenly through every part of the mould before cooling. Any mistake can ruin months of work. Even modern foundries occasionally encounter casting defects despite using sophisticated monitoring equipment. Yet the artisans responsible for the bronze head achieved exceptional results more than 2 millennia ago. Scientific analysis has shown that ancient bronze objects often required carefully balanced mixtures of copper and tin. Small variations could dramatically alter hardness, durability, casting behaviour and appearance. The creators of the Sooth's head clearly possessed extensive practical knowledge of metallurgy. The question is where that knowledge originated. Some scholars argue that Greek workshops produced the sculpture. Others believe Thracian artisans themselves reached a level of technical sophistication that historians have traditionally underestimated. The evidence remains inconclusive. Another mystery concerns the realism itself. The head is not an idealized ruler. It appears to depict an actual individual. Wrinkles, facial structure, and subtle anatomical details suggest direct observation. This raises a fascinating question. How did ancient sculptors achieve such accuracy? Did they work from life? Did they employ measurement techniques now lost? Did they use proportional systems comparable to those later described by classical artists? No records survive to explain their methods. The head becomes even more mysterious when compared to other technological achievements from antiquity. The builders of the Great Pyramid moved millions of stone blocks with methods still debated today. The creators of the Antikythera mechanism produced a machine containing more than 30 bronze gears, nearly 2,000 years before modern clockwork. Roman engineers developed marine concrete capable of surviving for millennia in seawater. The bronze head of Sooths III belongs in the same category of ancient accomplishments that appear far more advanced than many people expect. Perhaps the strangest detail is that the head was found separated from the statue. Archaeologists continue to debate why. One theory suggests ritual decapitation during funerary ceremonies. Another proposes symbolic transformation of the king into a heroic ancestor. Some researchers believe the separation occurred during later disturbances. None of these explanations has been conclusively proven. The mystery remains unresolved. Modern technology has provided new ways to study the artifact. Researchers have used microscopic examination, metallurgical analysis, high-resolution photography, digital modelling, and advanced conservation techniques. These methods reveal remarkable craftsmanship. They identify alloy characteristics. They expose manufacturing details invisible to the naked eye. Yet they cannot fully reconstruct the lost knowledge that produced the sculpture. What do you think is the greatest mystery of Sooths III's tomb? The engineering of the tomb, the lost wax casting technology, or the separated bronze head? Share your thoughts in the comments below. Frankshthi Cave sits on the coast of the Argolid Peninsula in southern Greece. Yet hidden inside this unremarkable limestone cave is evidence that may force historians to rethink the technological capabilities of prehistoric humans. Long before the pyramids, long before Stonehenge, and thousands of years before the first known Mediterranean civilizations, somebody living here was crossing open seas, navigating vast distances, and transporting valuable materials across the Aegean. The mystery is not that they survived, the mystery is how they did it. Archaeological excavations conducted between 1967 and 1979 revealed one of the longest continuous records of human occupation ever discovered in Europe. The cave preserves evidence spanning nearly 30,000 years, from roughly 38,000 BC to 3000 BC. Among the countless artifacts recovered, one category of material shocked researchers more than any other: volcanic glass, obsidian, and it came from an island that should have been unreachable. Francthy Cave contains thousands of obsidian tools and fragments. Chemical analysis revealed that much of this material originated from the island of Milos in the Aegean Sea. Today, Milos lies approximately 150 kilometers from Francthy by water. Even during the last ice age, when sea levels were significantly lower, Milos remained an island separated from mainland Greece by open water. This creates a remarkable problem. Obsidian appears at Francthy as early as approximately 13,000 years ago. That means prehistoric hunter-gatherers were somehow reaching an island located beyond the visible horizon, extracting volcanic glass and transporting it back across the sea. This was not a one-time event. The quantity of obsidian found in later layers suggests repeated journeys over many generations. To appreciate the significance of this achievement, consider that the earliest accepted evidence of organised seafaring in many parts of Europe appears much later. The people of Francthy may have been operating one of the oldest known maritime networks in the Mediterranean. Yet no boats survived, no harbours survived, and no navigation manuals survived. Only the obsidian remains, and it proves that somebody repeatedly crossed the sea. This may be the greatest mystery of Francthy Cave. Reaching Milos was difficult. Finding the way back was even more difficult. Modern sailors rely on compasses, maps, GPS satellites, weather forecasts, and centuries of accumulated nautical knowledge. The inhabitants of Francthy possessed none of these tools, yet they somehow travelled across waters that could easily become deadly. The fundamental question remains unanswered. How did they navigate? The curvature of the Earth creates a major challenge. At sea level, the visible horizon is only about 5 kilometers away. Even elevated islands disappear below the horizon at surprisingly short distances. In many conditions, sailors leaving one island could quickly lose sight of land altogether. Once surrounded by open water, there would be no obvious reference points. A minor navigational error of only a few degrees could result in missing a small island by many kilometers. Researchers have proposed several possibilities. One theory suggests that prehistoric sailors used the sun as a directional guide. The position of sunrise and sunset changes throughout the year, but experienced observers could potentially estimate direction with surprising accuracy. Another possibility involves celestial navigation. Long before written astronomy existed, humans may have learned to use recurring star patterns as orientation markers. Polynesian navigators crossed thousands of kilometers of Pacific Ocean using stars, wave patterns, cloud formations, and bird behavior without instruments. Some researchers wonder whether a simpler version of this knowledge existed in the prehistoric Aegean. A third possibility involves sea state observation. Modern indigenous navigators can detect subtle wave reflections caused by distant islands that remain invisible beyond the horizon. Certain wave patterns bend around land masses and create recognizable interference signatures. Could prehistoric sailors have learned to interpret these signals? No one knows. Even more puzzling is the question of knowledge transmission. A successful voyage could not depend entirely on luck. The same routes appear to have been used repeatedly over centuries. This implies that navigational knowledge was being taught, preserved, and passed between generations. but there was no writing, no charts, no maps, and no recorded instructions. The entire system existed only inside human memory. If Franchti's sailors truly crossed the Aegean regularly, they may have possessed one of the oldest sophisticated navigation traditions ever developed, and almost every detail of that tradition has vanished. The obsidian itself suggests something even more surprising: trade, or at least exchange. Obtaining obsidian required knowledge of distant locations, transporting it required planning, distributing it required social connections. This raises an extraordinary possibility. The Aegean Sea might already have contained a network of interacting communities thousands of years before the rise of classical Greek civilization. For decades, archaeologists viewed prehistoric hunter-gatherers as isolated groups with limited geographic reach. Franchti challenges that assumption. The cave suggests movement across hundreds of kilometers of coastline and sea. In effect, the Mediterranean may already have been functioning as a communication corridor long before cities existed. Franchti also records one of the most dramatic environmental transformations in human history. Around 20,000 years ago, global sea levels were more than 120 meters lower than today. As glaciers melted, coastlines shifted dramatically. Entire landscapes disappeared beneath rising waters. Harbours vanished. Migration routes changed. Ecosystems transformed. Yet the inhabitants of Franchti adapted successfully. They altered hunting strategies, exploited marine resources more intensively, and adjusted to changing environments over thousands of years. The remarkable question is how they tracked these environmental changes without scientific instruments. Their survival suggests generations of accumulated ecological knowledge. In many ways, they were conducting long-term environmental observation programs spanning centuries. Excavations have revealed evidence for the exploitation of large pelagic fish, including tuna. This discovery has major implications. Tuna are not easy coastal prey. Many species migrate seasonally and often travel through deeper offshore waters. Successfully targeting them requires timing, planning, and detailed knowledge of marine behaviour. Modern fisheries rely on sonar, satellite tracking, and biological surveys. The people of Franchti relied solely on observation, yet they managed to exploit resources that demanded a surprisingly sophisticated understanding of the sea. Some archaeologists describe this as a form of prehistoric applied science. Not science written in books, but science stored in experience. Perhaps the greatest mystery is not the voyages themselves. It is the disappearance of the knowledge that made those voyages possible. The inhabitants of Franchti understood navigation, marine ecology, resource management, tool production, and long-distance procurement. These were not simple survival skills. They represented an accumulated body of practical expertise developed across countless generations. Yet almost none of that knowledge survives. What do you think was the secret behind Franchti's ancient seafarers? Their boats, their navigation skills, or a lost system of knowledge we no longer understand? Share your thoughts in the comments below. Kurtvisi Fortress stands above the meeting point of the Mtkavari and Paravani rivers in southern Georgia. More than 1,000 years after its construction, the fortress still dominates one of the most strategic corridors in the Caucasus. Yet the greatest mystery is not who built it. The mystery is how its builders selected a location that appears almost perfectly optimized for defense, surveillance, logistics, and survival long before modern military engineering existed. Unlike many lost archaeological sites, Kurtvisi was never completely forgotten. Historical records mention the fortress as early as the medieval period, while archaeological investigations conducted during the 20th century reveal that portions of the site may rest upon much older foundations. What researchers discovered was not simply a fortress, but a remarkably sophisticated military system integrated directly into the surrounding landscape. The first and perhaps most astonishing mystery begins with a simple question. Why was Kurt-Visi built exactly here? At first glance, the answer appears obvious. The fortress occupies a rocky hill overlooking the confluence of two rivers. Throughout history, river junctions often became important economic and military locations. But the deeper researchers study the site, the more extraordinary the location becomes. Modern military analysts often evaluate defensive positions using three primary factors: visibility, accessibility, and natural protection. Kurt-Visi excels in all three. The fortress overlooks multiple valleys simultaneously, allowing anyone approaching from the east, west, north, or south to be observed long before reaching the walls. The surrounding rivers create natural barriers that reduce the number of directions from which attackers could launch effective assaults. Even more remarkable is the elevation. The fortress sits approximately 1,000 meters above sea level on terrain that naturally limits large-scale troop movements. Ancient armies often depended upon mass formations, but steep slopes disrupted those formations and reduced the effectiveness of siege operations. Researchers using modern topographic mapping have observed that the fortress occupies one of the most advantageous positions in the entire river corridor. In military terms, it functions almost like a natural command center. This raises an uncomfortable question. How did medieval engineers identify such an optimal location without aerial surveys, satellite imagery, topographic maps, or modern geographic analysis? Today, military planners use drones, GIS software, digital elevation models, and computer simulations to evaluate terrain. The builders of Kurt-Visi possessed none of these technologies, yet their final choice appears remarkably close to what modern analysis would recommend. Some researchers argue that centuries of accumulated local knowledge may explain the decision. Others suggest that generations of observation gradually revealed the strategic value of the location. Regardless of the explanation, the precision of the choice remains one of the fortress's greatest mysteries. The comparison with other famous strongholds is striking. Machu Picchu occupies a mountain ridge controlling key Andean routes. Masada overlooks the Judean desert from a nearly inaccessible plateau. Narinkala Fortress dominates the narrow Caspian corridor, known as the Caspian Gate. Kurt-Visi belongs in the same category of exceptionally strategic sites, where geography itself became the primary defensive weapon. Choosing the location was only the beginning. Constructing a fortress there created another challenge. The steep terrain provided defensive advantages, but it also created enormous logistical problems. Thousands of tons of stone had to be transported uphill. Construction materials, food supplies, timber, tools, and water all needed to reach the site. Even today, transporting heavy materials through mountainous terrain requires specialized equipment. Yet, medieval builders completed the project centuries before mechanized transportation. Archaeologists have identified extensive stonemasonry integrated directly into the natural bedrock. Rather than leveling the landscape, builders adapted their structures to the existing terrain. This approach reduced material requirements while increasing stability. The technique resembles strategies later observed at Machu Picchu, where Inca engineers incorporated natural rock formations into their architecture rather than attempting to reshape entire mountains. The question remains unanswered. How was construction organized on such difficult terrain? No surviving engineering manuals describe the process. The Caucasus is not a geologically quiet region. Georgia has experienced numerous earthquakes throughout recorded history. Many structures constructed in similar conditions have collapsed long ago. Kurt-Visi remains standing. Some sections have suffered damage over the centuries, but large portions of the fortress continue to survive. researchers have noted several potentially important characteristics. The walls often follow the contours of the landscape rather than imposing rigid geometric patterns. Irregular layouts may help distribute stresses more effectively during seismic activity. Many stones are large and carefully fitted, while thick walls create substantial mass and stability. Whether these features represent intentional earthquake-resistant engineering or fortunate design choices remains debated. The comparison with Inca stonework is particularly interesting. At Machu Picchu and Sacsayhuaman, precisely fitted stones helped structures withstand repeated earthquakes. Kürtvissi does not employ the same masonry techniques, but both sites demonstrate that ancient builders often possessed a sophisticated understanding of structural behaviour long before formal engineering science emerged. Every fortress faces the same challenge: water. Without a reliable water supply, even the strongest defensive position eventually falls. The problem becomes especially severe during sieges. Historical examples demonstrate this repeatedly. Many seemingly impregnable castles were ultimately defeated not through direct assault, but through starvation and dehydration. Kürtvissi overlooks rivers, but accessing river water from a fortified hill during wartime would have been dangerous. Evidence suggests that the fortress contained storage systems designed to collect and preserve water. Researchers have identified cisterns and possible rainwater management features. Yet the complete hydraulic system remains poorly understood. How much water could the fortress store? How long could defenders survive under siege conditions? These questions remain largely unanswered. Another intriguing mystery involves visibility. The fortress occupies a position with extensive views across the surrounding landscape. Many historians believe medieval Georgia maintained systems of visual communication using fire and smoke signals. Kürtvissi may have served as one node within a larger defensive network stretching across the region. If true, the fortress functioned not merely as a defensive structure but as an information processing centre. Warnings could potentially travel across vast distances far faster than messengers on horseback. The concept resembles beacon networks used by the Byzantines, Romans, and later medieval kingdoms throughout Eurasia. Exactly how the system operated remains uncertain. Perhaps the greatest mystery is not the fortress itself. It is the disappearance of the expertise that created it. The builders of Kürtvissi understood terrain analysis, structural engineering, logistics, water management, military architecture, and large-scale construction. They successfully transformed one of the most difficult landscapes imaginable into a durable defensive complex. Yet almost none of their technical explanations survive. No engineering plans remain, no construction manuals survive, no detailed records explain how site selection decisions were made. What do you think was Kürtvissi's greatest secret? The choice of its nearly perfect location, its engineering, or the lost knowledge behind its construction? Share your thoughts in the comments below. Southern Albania, a long ridge overlooking the Drino Valley. Hidden beneath centuries of vegetation and abandonment stood the ruins of Phoenix, once the largest city of ancient Epirus. Archaeological investigations beginning in the 19th century and continuing through modern Italian and Albanian excavations revealed an enormous fortified city covering more than 50 hectares. Massive stone walls, public buildings, temples, reservoirs, and one of the largest theatres in the region emerged from the earth. What archaeologists expected to find was another ancient city. What they found instead was evidence of engineering capabilities that remain only partially understood. More than 2,300 years ago, the builders of Phoenix transformed a rugged mountain ridge into a heavily fortified urban centre capable of supporting thousands of inhabitants. Today, the ruins continue to raise questions about construction, methods, surveying techniques, logistics, water management, and architectural knowledge that historians still cannot fully explain. The first mystery begins with geography. Phoenice occupies one of the most strategically advantageous locations in the Balkans. The city sits roughly 270 meters above sea level, commanding views across the surrounding valleys and major travel corridors. From its elevated position, inhabitants could monitor movement for many kilometers in multiple directions. At first glance, this may seem like an obvious military choice. The mystery is how accurately ancient planners identified the location's advantages long before aerial mapping, satellite imagery, or modern topographic analysis existed. Modern military planners use computer-generated terrain models to evaluate visibility and defensive potential. Yet, studies of Phoenice suggest its builders selected a position that maximized observation while minimizing vulnerability. Comparable examples exist at Mycenae in Greece, Masada in Israel, and Machu Picchu in Peru. However, Phoenice's ridgetop position appears particularly optimized for regional control. Archaeologists continue to debate whether ancient surveyors relied solely on direct observation or possessed more sophisticated methods of landscape analysis that have disappeared from history. The most striking feature of Phoenice is its enormous defensive wall system. Some sections extend for several kilometers around the city. The walls consist of massive limestone blocks fitted together using polygonal masonry, a technique in which irregular stones are carefully shaped to interlock with extraordinary precision. Many individual blocks weigh several tons. What puzzles engineers is the accuracy. Modern measurements show that numerous joints fit so tightly that only extremely thin gaps remain between adjacent stones. This level of precision required repeated shaping, testing, adjustment, and repositioning. The challenge becomes even more impressive when considering the tools available. The builders possessed no steel cutting equipment, hydraulic machinery, powered cranes, or laser-guided measuring systems. Yet the finished result rivals masonry seen at Mycenae, Tiryns, and even certain Inca structures such as Sacsayhuaman. Experimental archaeologists attempting to recreate polygonal masonry have discovered that achieving such precision is extraordinarily labour-intensive. Even with modern tools, producing perfectly fitted stone joints requires significant expertise. This raises an unanswered question. How did Phoenice's builders develop and maintain such advanced stoneworking knowledge across multiple generations? No technical manuals survive. No construction records survive. Only the stones remain. The walls create another engineering puzzle. Before the stones could be assembled, they first had to reach the construction site. Researchers estimate that many blocks weigh between 2 and 5 tons, while some may exceed 10 tons. Transporting such masses uphill across rugged terrain represents a major logistical challenge even today. The nearest quarries provided suitable limestone, but moving thousands of tons of material from quarry to ridgetop city would have required a highly organized workforce. Ancient Egyptian builders transported blocks for the pyramids using sledges, ramps, and large labor teams. Roman engineers employed sophisticated lifting devices powered by pulleys and treadwheel cranes. For Phoenice, the exact methods remain uncertain. Very little physical evidence survives for the transportation infrastructure that must once have existed. Were temporary roads constructed? Were wooden rollers used? Did seasonal weather conditions influence construction schedules? The answers remain largely unknown. Southern Albania lies within a seismically active region. Over the last 2 millennia, the area has experienced numerous earthquakes capable of damaging or destroying stone structures. Yet substantial portions of Phoenice's walls remain standing. This survival has attracted increasing attention from structural engineers. One possible explanation involves the polygonal masonry itself. Unlike rigid modern concrete walls, polygonal structures distribute stress through multiple contact points. During seismic activity, slight movement can occur without immediately producing catastrophic failure. Researchers studying Inca architecture in Peru have observed similar behaviour. Some Inca walls survived major earthquakes that damaged later colonial buildings. Finis may represent another example of this phenomenon. The mystery is whether the builders intentionally designed for seismic resilience or accidentally discovered principles that modern engineering would only later formalize mathematically. No written evidence currently provides a definitive answer. A city cannot survive without water. Finis presents a significant challenge because of its elevated position. Transporting water uphill on a daily basis would have been inefficient and impractical for a large urban population. Excavations have revealed reservoirs, cisterns, and water storage systems distributed throughout the city. These discoveries demonstrate careful planning. The annual rainfall of southern Albania averages approximately 1,000 millimeters. While substantial, rainfall alone cannot guarantee a stable supply throughout seasonal fluctuations. The builders therefore needed systems capable of collecting, storing, and distributing water efficiently. Comparisons have been made with Petra in Jordan, where Nabatean engineers developed sophisticated water harvesting technologies, and with ancient Pergamon in Anatolia, whose inhabitants constructed advanced hydraulic systems. Finis appears less technologically dramatic than those sites. Yet many details remain poorly understood. How much water could the reservoir store? How were losses from evaporation minimized? How was water quality maintained? Researchers continue investigating these questions. One of the most surprising discoveries at Finis is the scale of urban organization. The city included residential districts, administrative structures, religious buildings, storage facilities, public spaces, and a large theatre. Constructing such a complex settlement on uneven terrain required extensive planning. Today, urban planners rely on digital terrain models, engineering software, and geographic information systems. Ancient planners had none of these tools, yet Finis demonstrates careful integration between architecture and landscape. Roads connect different sectors efficiently. Major structures occupy advantageous positions. Defensive considerations appear integrated into the city's overall design. The result suggests a level of planning sophistication that exceeds common assumptions about regional settlements during the Hellenistic period. Among Finis's most remarkable structures is its theatre. The theatre ranks among the largest ancient theatres discovered in the region and could accommodate thousands of spectators. Like many Greek theatres, it raises questions about ancient acoustic knowledge. Modern acoustic engineers use mathematical modelling, computer simulations, and advanced materials testing to optimize sound transmission. Ancient builders possessed none of these resources, yet performances remained intelligible to audiences seated considerable distances from the stage. Research conducted at comparable Greek theatres has demonstrated that architectural geometry can naturally amplify certain frequencies associated with human speech. Whether ancient architects understood these principles theoretically or discovered them through centuries of experimentation remains uncertain. Finis may preserve evidence of one of the world's earliest forms of large-scale acoustic engineering. The city itself poses a final logistical question. Finis was not a small village. At its peak, it served as a major political and economic centre for the Chaonians and later played an important role within the broader Hellenistic and Roman worlds. Large-scale construction projects require resources. Stone must be quarried, workers must be fed, tools must be manufactured, infrastructure must be maintained. All of this implies a sophisticated economic network. Archaeological evidence suggests connections extending throughout Epirus and beyond. Trade routes linked the city with coastal regions, inland communities, and Mediterranean markets. Yet, historians still debate the true scale of Phoenix's economy. How large was its population? How many workers participated in major construction projects? How were labour forces organised? The archaeological record provides clues, but not complete answers. The ruins of Yamchun Fortress stand in the Pamir Mountains of eastern Tajikistan at an elevation exceeding 3,000 metres above the Wakhan Valley. Perched on a narrow ridge overlooking one of Central Asia's most important historical corridors, the fortress commands views stretching for dozens of kilometres across the valley below. Although local legends connect the site to ancient kings and forgotten empires, archaeologists generally believe Yamchun was occupied and expanded between roughly the 3rd century BC and the early medieval period. The fortress attracted significant scholarly attention during surveys of the Wakhan corridor, where researchers realised that its strategic position was unlike almost any other fortification in Central Asia. What they discovered was not merely an ancient fortress, it was an engineering mystery. Even today, many fundamental questions remain unanswered. How was such a massive structure built on an isolated mountain ridge? How were construction materials transported to such extreme elevations? How did its builders understand the landscape so well that they created one of the most strategically positioned fortresses in the ancient world? The deeper researchers investigate Yamchun, the more remarkable the mysteries become. The first mystery begins with the mountain itself. Yamchun occupies a ridge rising dramatically above the Wakhan Valley, a historic route that connected regions of modern Tajikistan, Afghanistan, China, and Central Asia. From the fortress, observers could monitor movement across vast sections of the valley floor. Modern military analysts often emphasize the importance of high ground, yet Yamchun seems to take this principle to an extreme. Researchers using satellite imagery and digital terrain modelling have shown that the fortress occupies one of the most advantageous defensive locations in the region. Steep cliffs protect several sides naturally, leaving attackers with only a few viable approaches. The question is how ancient builders identified such a location. Today, military planners use aerial reconnaissance, topographic maps, GPS systems, and computer simulations, but the engineers of Yamchun possessed none of these technologies. Yet they selected a position that appears optimized for surveillance, defense, communication, and resource control. This raises a fascinating possibility. Did the builders possess generations of accumulated surveying knowledge that has since disappeared? The mystery becomes even greater when compared with other mountain fortresses. Sites such as Machu Picchu and Masada occupy similarly strategic terrain, but Yamchun was constructed in one of the most rugged mountain environments on Earth. The second mystery concerns logistics. The fortress walls stretch across hundreds of meters and include numerous towers, defensive structures, and extensive stonework. Constructing such a complex required enormous quantities of building material. Today, heavy machinery would be used to transport stone up steep mountain slopes, but ancient builders had no cranes, trucks, or powered equipment. Archaeologists estimate that even relatively small mountain fortifications often required thousands of tons of stone. Every block used at Yamchun had to be quarried, shaped, transported, and positioned under extremely difficult conditions. Experimental archaeology demonstrates how challenging this process would have been. Moving a single stone block weighing 1 ton can require dozens of workers on level ground, and on steep mountain terrain the difficulty increases dramatically. Yet Yamchun was completed. No surviving records explain how construction teams organised labour, maintained supply chains, or transported materials. The engineering system behind the fortress has vanished, leaving only the final result. One of the most overlooked features of Yamchun is the shape of its walls. Unlike many ancient fortifications built around geometric plans, Yamchun follows the contours of the mountain itself. The walls bend, curve, and adapt to the natural landscape with remarkable precision. This design was not accidental. Modern defensive engineering recognizes that terrain can function as a force multiplier. A wall positioned correctly along a ridge can dramatically increase defensive effectiveness while reducing construction requirements. The builders appear to have understood this principle. Several sections of the fortress exploit natural cliffs, reducing the need for artificial barriers, while other sections direct potential attackers toward predictable routes where defenders would have enjoyed significant advantages. The result resembles a carefully planned military system rather than a simple fortress. What remains unclear is how ancient engineers measured and analysed such a complex landscape without modern surveying equipment. Among Yamchun's most distinctive features are its defensive towers. Many surviving towers project outward from the walls, creating overlapping fields of observation and defence. This concept appears simple, but in reality it represents sophisticated military engineering. A projecting tower allows defenders to observe areas directly below the walls, eliminating dangerous blind spots. It also enables crossfire against attackers approaching from multiple directions. Centuries later, similar principles became standard in medieval castles throughout Europe and Asia. Yet Yamchun demonstrates these concepts long before many later fortification systems emerged. The mystery is not whether the towers worked. The mystery is how their builders discovered such effective defensive geometry. Did they learn through centuries of military experience? Was there a lost tradition of fortress engineering? Or did multiple civilizations independently develop similar solutions to the same defensive problems? No definitive answer exists. The Pamir Mountains are one of the most seismically active regions in Asia. Earthquakes have shaped the landscape for millions of years, and any large structure built in this environment faces constant geological threats. Yet portions of Yamchun have survived for centuries. This survival has attracted increasing interest from engineers. Many ancient civilizations struggled with earthquakes. Some structures collapsed after only a few generations, while others developed unexpected resilience. Researchers studying surviving sections of Yamchun have noted thick walls, layered construction techniques, and extensive use of local materials. These characteristics may have contributed to structural stability. The situation recalls other ancient engineering puzzles. In Peru, Inca stonework demonstrates extraordinary seismic resistance. In Japan, some traditional wooden temples have survived repeated earthquakes. In the Mediterranean, certain Roman structures continue standing after nearly 2,000 years. Yamchun may belong within this same category of forgotten engineering achievements. Unfortunately, no technical documents survive to explain the builder's methods. Perhaps the most intriguing possibility is that Yamchun was never intended to operate alone. The fortress occupies a position that would have been ideal for visual communication across the Wakhan region. Ancient civilizations often relied on signal systems using fires, smoke, reflective surfaces, or beacon towers. The Persian Empire operated communication networks spanning thousands of kilometers. The Romans developed frontier warning systems. The Great Wall of China incorporated signal towers capable of transmitting alerts rapidly across vast distances. Some researchers suspect Yamchun may have participated in a similar network. If true, remarkable questions emerge. How far could signals travel between mountain fortresses? How quickly could warnings move across the region? Did standardized communication protocols exist? No direct evidence has yet provided definitive answers. Nevertheless, the fortress's location strongly suggests that long-distance observation and communication played important roles in its design. Every fortress depends upon water. This requirement becomes especially challenging at high elevations. A large garrison could require thousands of litres of water every day, and during a siege, access to reliable water supplies often determined survival. Near Yamchun are natural springs and water sources that may have supported occupation of the site. Archaeologists have identified indications of water management systems, but the complete design remains uncertain. This creates another engineering puzzle. How did fortress inhabitants collect, store, distribute and protect water in an environment characterized by harsh winters, extreme temperature fluctuations, and limited resources? Ancient hydraulic systems elsewhere continue to astonish researchers. The Khanats of Persia transported groundwater across deserts. Roman aqueducts carried water hundreds of kilometers. The Nabateans developed sophisticated water storage technologies in arid environments. Yamchun may represent another example of advanced hydraulic knowledge that has only partially survived. Matala Caves are located in southern Crete, Greece. Rising above the waters of Matala Bay is a honeycomb-like cliff containing dozens of artificial chambers carved directly into soft sandstone. Archaeologists have studied the site since the 19th century, and excavations have revealed that many of the caves were used during the Roman period, particularly between the 1st century BC and the 2nd century AD. Yet despite more than a century of investigation, researchers still cannot fully explain how ancient builders created such an extensive cliffside complex with the technology available at the time. The caves are often described as Roman tombs, but the reality may be far more complicated. Behind their simple appearance lies a series of engineering puzzles involving surveying, rock cutting, structural stability, and large-scale planning that remain only partially understood today. At first glance, Matala appears to be nothing more than a collection of random openings in a rock face, but closer examination reveals something very different. More than 60 artificial caves are distributed across a sandstone cliff overlooking the Mediterranean. Many contain multiple chambers, carved entrances, windows, benches, niches, and interconnected rooms. Some are positioned several meters above sea level, while others occupy locations that would have required dangerous access during construction. Creating a single chamber in rock is difficult enough, but constructing dozens of chambers across a vertical cliff face requires long-term planning, labor organization, and engineering knowledge. Researchers estimate that thousands of cubic meters of sandstone were removed. Even relatively soft sandstone requires continuous cutting, shaping, and debris removal, and without modern machinery, every cubic meter would have been excavated manually using iron tools. This raises an obvious question: who coordinated such a project? No surviving inscriptions identify the engineers, and no construction records describe the work. The people responsible for transforming the cliff into a massive architectural complex remain unknown. The situation resembles other famous rock-cut monuments such as Petra in Jordan, the Ajanta caves in India, and the rock-hewn churches of Lalibela in Ethiopia. In every case, archaeologists can study the finished structures while knowing remarkably little about the engineering teams that created them. Perhaps the greatest technical mystery concerned the excavation process itself. Modern engineers examining the site face a fundamental problem. There are several possible ways to create chambers inside a cliff, but each method presents serious difficulties. If workers carved directly into the cliff from the front, they would have required extensive scaffolding. Building stable wooden platforms against a steep coastal rock face would have demanded careful planning and enormous quantities of timber. If workers approached from above using ropes, they would have needed advanced techniques for positioning labourers and removing excavated stone. If they combined both methods, the logistics become even more complicated. Archaeologists have identified tool marks throughout the caves, confirming that iron implements were used extensively. However, the exact sequence of excavation remains uncertain. Experimental archaeologists attempting to recreate ancient rock-cutting techniques have discovered that progress is far slower than most people imagine. Removing even a few cubic meters of stone can require hundreds of labour hours, and scaling that effort to the entire Matala complex suggests a massive investment of time and manpower. Yet no historical source explains how the work was organised. The cliff preserves the result, but not the process. One of the most overlooked mysteries involves geometry. Many chambers display surprisingly regular dimensions. Doorways align with interior spaces, niches appear deliberately positioned, and certain cave groups follow recognisable patterns rather than random placement. This implies some form of surveying. Today, engineers rely on laser measurements, digital models, and precise instruments. But ancient builders possessed none of these tools. Even so, they still had to answer critical questions. How far should each chamber extend into the rock? How could they avoid accidentally breaking into neighbouring chambers? How did they maintain alignment while excavating spaces that could not be fully observed from the outside? Researchers studying ancient construction have repeatedly encountered similar puzzles. The builders of the Egyptian pyramids maintained remarkable precision across millions of stone blocks. Roman engineers constructed aqueducts with gradients measured in centimetres per kilometre. The craters of underground cities such as Derinkuyu in Turkey excavated vast networks without modern surveying equipment. Matala may represent another example of sophisticated practical geometry whose exact methods have been lost. The traditional explanation identifies many caves as Roman burial chambers. Archaeological evidence certainly supports funerary use. Several caves contain features commonly associated with tombs, and artifacts discovered during excavations indicate burial activity. Yet some researchers question whether this explanation tells the entire story. Certain chambers possess layouts that appear unusually complex for simple tombs. Multiple rooms, carved benches, and enlarged interior spaces suggest that at least some caves may have served additional functions. They may have been temporary dwellings, storage facilities, religious chambers, or meditation spaces. The debate continues because physical evidence can support more than one interpretation. This uncertainty is not unique to Matala. Similar disagreements surround numerous ancient sites, including parts of Petra, Cappadocia, and various rock-cut settlements throughout the Mediterranean. The caves may represent a combination of functions developed over centuries rather than a single purpose. The sandstone cliff itself presents another puzzle because not all rock behaves the same way. Modern geological surveys reveal variations in density, fracture patterns, weathering resistance, and structural stability across coastal sandstone formations. Choosing the wrong location for excavation can lead to collapse. Yet, many Matala chambers have survived for nearly 2,000 years. This suggests that the builders understood far more about the rock than simple trial and error. Before carving each chamber, they likely evaluated the strength of the stone, the direction of natural fractures, the risk of roof failure, the effects of water infiltration, and the long-term stability of the cliff face. Modern mining engineers perform similar assessments using geological mapping, core samples, and structural analysis software, whereas ancient builders relied entirely on observation and accumulated experience. The fact that so many chambers remain intact indicates an impressive level of practical geological knowledge. The Mediterranean coastline is an aggressive environment. Salt crystallization, wind erosion, temperature fluctuations, and moisture gradually destroy exposed rock surfaces, and over centuries these processes can dramatically alter entire landscapes. Yet large portions of Matala remain recognizable after nearly 2 millennia. Scientists studying sandstone weathering have found that coastal erosion rates can vary significantly depending on mineral composition and environmental conditions. Even small differences in rock structure can determine whether a surface survives for centuries or disintegrates relatively quickly. This creates a fascinating question. Did the ancient builders intentionally select the most durable portions of the cliff? Or were they simply fortunate? Some geological evidence suggests that specific sections of the sandstone formation possess superior structural characteristics. If the builders recognized these differences, they may have been making sophisticated engineering decisions long before geology became a formal science. Perhaps the most difficult mystery involves access. Many caves occupy positions that appear challenging even today. Modern visitors use pathways, stairs, and safety infrastructure, but ancient workers had none of these advantages. To excavate chambers several meters above ground, labourers would have needed scaffolding, rope systems, material transport methods, safety procedures, and communication systems. All of these technologies leave surprisingly little archaeological evidence. Wood decays, rope disappears, and temporary structures vanish. As a result, researchers can study the chambers themselves, but rarely the equipment used to create them. The same problem affects investigations at Petra, Cappadocia, and numerous cliffside monasteries throughout the ancient world. The structures survive while the engineering systems that enable their construction are almost entirely lost. What do you think was the most impressive achievement behind the Matala caves? The surveying, the excavation, or the cliffside engineering? Share your thoughts in the comments below. Arbor Low stands on a windswept limestone plateau in Derbyshire, England, within the Peak District National Park. Often called the Stonehenge of the North, the monument consists of approximately 50 massive limestone blocks arranged within a circular earthwork nearly 100 meters in diameter. Unlike Stonehenge, however, every major stone lies flat on the ground. The site was first documented by antiquarians during the 17th century and later studied by archaeologists throughout the 19th and 20th centuries. Modern excavations, radiocarbon dating, geophysical surveys, aerial photography and LiDAR mapping have revealed that Arbor Low was constructed around 2500 to 2000 BC, placing it among Britain's most important prehistoric monuments. Yet despite centuries of research, Arbor Low remains one of Europe's greatest engineering mysteries. The question is surprisingly simple. How did a farming society with no metal tools, no written language, no wheeled transport and no advanced machinery create one of the largest ceremonial monuments in prehistoric Britain? And perhaps even more puzzling, why does it look so different from every other famous stone circle? The first mystery appears immediately. Most stone circles were built around upright megaliths. Stonehenge, Avebury, Castlerigg and dozens of other monuments across Britain feature standing stones that define ceremonial space. Arbor Low does not. Its stones lie horizontally, scattered around the circle like the remains of a forgotten catastrophe. For centuries, researchers assumed the stones had originally stood upright before collapsing over time. That explanation seems reasonable. as weathering, erosion, earthquakes, or human activity could have caused the stones to fall. But excavations produced a problem. Archaeologists have struggled to identify convincing evidence for the deep foundation pits normally required to support multi-ton standing stones. At Stonehenge, the sockets used to anchor the stones are obvious. At Arbor, the evidence is far less clear. This has generated a controversial alternative theory. What if the stones were never intended to stand upright at all? If true, Arbor would represent a completely different architectural tradition. The monument may have been designed around horizontal stones from the beginning, suggesting a ritual or symbolic purpose that modern archaeology does not yet understand. No one knows which explanation is correct. More than 4,000 years after construction, the monument still refuses to reveal its original appearance. Regardless of whether the stones stood upright, moving them was an extraordinary achievement. Most of Arbor stones are limestone slabs weighing between several and many tons each. Together they form a ring approximately 90 meters across. The builders had no iron tools, no steel cables, no cranes, and no wheeled vehicles capable of carrying such loads. Experimental archaeology has shown that moving even a single multi-ton stone using prehistoric technology requires large teams of workers, wooden sledges, rollers, ropes, and carefully prepared routes. Researchers recreating megalith transport experiments have found that dozens of people may be required to move stones weighing only a few tons over relatively short distances. At Arbor, roughly 50 stones had to be quarried, transported, positioned, and arranged according to a carefully planned geometric design. The logistical challenge rivals projects found at Stonehenge and Avebury. This raises a fundamental question. How large and organised was the society responsible for the monument? Traditional models once portrayed Neolithic communities as small farming groups operating independently. Arbor suggests something different, a society capable of coordinating large labour forces, managing resources, and executing construction projects that may have taken years or even generations to complete. One of the least appreciated mysteries involves geometry. Viewed from the air, Arbor appears remarkably organised. The monument consists of a circular ditch surrounded by a substantial bank, enclosing an oval arrangement of stones. The overall design displays a level of planning that should have been difficult to achieve using simple prehistoric tools. Modern engineers rely on surveying instruments, laser measurements, GPS systems, and digital mapping. The builders of Arbor possessed none of these technologies, yet they created an earthwork approximately 100 meters across with impressive geometric consistency. To understand the challenge, imagine attempting to mark a nearly perfect circle across uneven terrain using only wooden stakes, rope, and visual observation. Small errors accumulate rapidly, and over long distances, maintaining symmetry becomes increasingly difficult. Nevertheless, Arbor exhibits a level of precision suggesting that its builders possessed sophisticated practical knowledge of measurement and landscape surveying. Exactly how that knowledge was transmitted remains unknown. No written manuals survive, no diagrams survive, and no technical instructions survive. The geometry exists, but the engineering knowledge behind it does not. The ditch surrounding Arbor creates another mystery. The monument belongs to a class of prehistoric structures known as henges. What makes henges unusual is that their defensive logic appears backwards. In military fortifications, defenders typically stand behind a ditch, forcing attackers to cross a difficult obstacle before reaching the walls. At Arbor, the ditch lies inside the bank. Anyone approaching from outside would actually stand on a higher ground than anyone inside. From a defensive perspective, the design is irrational. This strongly suggests that the monument was never intended as a fortress. But if defence was not the goal, why invest enormous effort excavating thousands of tons of earth? Calculations indicate that constructing the ditch and bank would have required moving vast quantities of material, using nothing more than antler picks, wooden tools, and human labour. The purpose remains uncertain. Some researchers suggest the earthworks created a symbolic boundary separating sacred and ordinary space. Others believe the design controlled movement during ceremonies. Still others propose functions related to astronomy, social gatherings, or ritual performances. No explanation fully accounts for every feature of the site. Many prehistoric monuments across Britain exhibit clear astronomical relationships. Stonehenge famously aligns with the summer solstice sunrise. Newgrange in Ireland captures sunlight during the winter solstice. Numerous stone circles appear connected to lunar cycles, seasonal events, or celestial observations. Arbor Low presents a more difficult puzzle. Various researchers have proposed alignments involving solstices, lunar standstills, and significant horizon events. Some observations appear promising, while others fail statistical testing. Unlike Stonehenge, Arbor Low lacks a universally accepted astronomical interpretation. This uncertainty has led to a fascinating possibility. Modern researchers may be looking for the wrong celestial pattern. Ancient observers did not necessarily organize the sky according to modern categories. Their system may have incorporated combinations of solar, lunar, seasonal, environmental, and ritual observations that no longer survive. If Arbor Low functioned as an astronomical monument, the knowledge required to understand it may have disappeared thousands of years ago. The stones remain, but the code may be lost. Recent studies at prehistoric monuments have introduced an entirely different possibility: sound. Experiments conducted at stone circles throughout Britain have demonstrated that monument geometry can influence acoustics. Echoes, resonances, reflections, and sound amplification sometimes occur in unexpected ways. Arbor Low occupies a prominent elevated location exposed to wind and open landscapes. Researchers have questioned whether the site's placement was influenced partly by acoustic considerations. Could chanting, drumming, or ceremonial gatherings have interacted with the monument's shape? Could sound have played a role as important as visual appearance? Definitive evidence remains elusive. Yet the question highlights an important reality. Ancient builders may have understood environmental effects that modern archaeology is only beginning to investigate. Perhaps the most extraordinary puzzle is not technological at all. It is organisational. Every stone moved, every ditch excavated, every measurement made, and every ceremony performed required cooperation. Arbor Low demonstrates that prehistoric communities possess the ability to mobilise labour on a remarkable scale. The monument required planning, leadership, resource management, food production, technical knowledge, and long-term coordination. These are characteristics normally associated with complex societies. Yet Arbor Low predates cities, states, and written administration in Britain. How was such coordination achieved? Who directed construction? How were skills transmitted? How were standards maintained across years of work? The archaeological record provides few answers. Southwestern Albania. At the southern end of the Bay of Law, where the Adriatic Sea meets the Ionian Sea, lie the ruins of Oricum, one of the most strategically positioned ports of the ancient Mediterranean. Although ancient authors, including Julius Caesar, mentioned the city during the Roman Civil War, the true scale of Oricum remained poorly understood until systematic archaeological investigations began during the 20th century. Excavations revealed a surprisingly sophisticated harbour city hidden beneath layers of sediment, marshland, and changing coastlines. What researchers discovered was not simply another ancient port, but evidence of a maritime engineering system whose most important technologies remain only partially understood. Today, many of Oricum's greatest mysteries are not found in its temples or public buildings. They are found in the harbour itself. Modern port engineers spend years studying wave energy, coastal erosion, currents, sediment transport, water depth, and weather patterns before selecting a harbour location. The builders of Oricum somehow accomplished something remarkably similar more than 2,000 years ago. The city occupied a narrow zone between mountains, lagoon systems, and open sea. To the west stood the Karaburun Peninsula, forming a natural barrier against powerful Adriatic storms, while to the east lay protected inland waters. The surrounding geography created one of the safest natural anchorages in the entire region. Even today, satellite imagery demonstrates how effectively the landscape shields the bay from major wave action. What makes this extraordinary is that ancient surveyors possessed no satellites, no hydrographic maps, no computer simulations, and no meteorological databases. Yet their choice rivaled some of the most successful harbour locations of the ancient world. Researchers often compare Oricum to the harbours of Alexandria in Egypt, Piraeus in Greece, and Ostia near Rome. All became major maritime centres because their builders understood geography exceptionally well. The question remains: how did Oricum's planners acquire such precise environmental knowledge? Some archaeologists believe generations of sailors accumulated observational data over centuries, while others argue that ancient Mediterranean navigators possessed a far deeper understanding of coastal dynamics than traditionally assumed. The truth remains uncertain. One of the strangest discoveries at Oricum involves the coastline itself. When the city flourished, much of the harbour sat directly beside navigable waters. Today, large portions of the ancient waterfront lie separated from the sea by accumulated sediment and marshland. Geological studies indicate that the shoreline has shifted dramatically over the last 2 millennia. This presents a major puzzle. Sedimentation is one of the greatest threats facing any harbour. Rivers transport enormous quantities of sand, silt, and clay into coastal environments. Over time, these materials accumulate, gradually reducing water depth until ports become unusable. Modern harbours spend millions of dollars annually on dredging operations to prevent this process. Ancient Oricum somehow remained operational for centuries, despite facing the same challenge. How? One possibility is that engineers understood how to exploit natural currents to flush sediment away from harbour entrances. Similar strategies were employed centuries later in Venice and several medieval Mediterranean ports. Another possibility is that large-scale dredging operations occurred regularly. The problem is that direct archaeological evidence remains limited. Researchers know the harbour functioned successfully. What they do not know is exactly how its operators prevented nature from destroying it. Perhaps the most overlooked technological mystery at Oricum involves maintenance. Ancient ships required specific water depths for safe navigation. Large Roman merchant vessels could reach lengths exceeding 30 metres and carry cargoes weighing hundreds of tons. Some grain ships travelling between Egypt and Rome may have displaced more than 1,000 tons. Such vessels could not simply enter shallow coastal waters. Maintaining navigable channels required continuous management. Today, engineers use sonar mapping, dredging vessels, GPS positioning systems, and hydraulic modelling. Ancient harbour administrators had none of these tools. Yet Oricum continued serving maritime traffic for generations. This raises an important question. Did ancient engineers possess harbour maintenance techniques that have largely disappeared from historical records? several Mediterranean ports show evidence of sophisticated dredging practices. The famous Roman harbour of Portus required constant sediment management. Similar challenges existed at Ephesus, whose harbour eventually became unusable after severe silting. Oricum may represent another example of technological expertise that left few written descriptions but substantial physical results. Modern coastal engineering relies heavily on mathematics. Engineers model wave energy, tidal interactions, sediment transport, and current velocities using advanced equations and computer simulations. The people of Oricum possessed none of these technologies. Nevertheless, they successfully built and maintained infrastructure in one of the most dynamic environments on Earth. The sea constantly changes. Currents shift, storms alter shorelines, and sediment moves unpredictably, yet the harbour survived. This suggests something remarkable. Ancient maritime communities may have developed extensive empirical knowledge systems based entirely on long-term observation. A sailor who spends decades navigating the same coastline can learn extraordinary amounts about wave behaviour, seasonal winds, and current patterns. Multiply that knowledge across generations and a surprisingly sophisticated engineering tradition becomes possible. In some respects, Oricum challenges modern assumptions about the relationship between science and practical expertise. Harbour cities face a difficult environmental problem. They must remain close to water while simultaneously protecting themselves from water. Excavations at Oricum have uncovered public buildings, roads, and urban infrastructure that existed within a landscape vulnerable to flooding, groundwater intrusion, and seasonal environmental fluctuations. This suggests the presence of drainage systems that are still not fully understood. Roman engineers were famous for aqueducts, sewers, and hydraulic projects, yet many components of Oricum's water management network remain buried beneath sediment. Researchers suspect that undiscovered channels and drainage structures may still exist beneath the site. If confirmed, they could reveal how ancient engineers controlled water levels within a coastal city long before modern hydraulic engineering emerged. Saltwater is one of the most destructive environments for construction materials. Moisture penetrates stone, salt crystals expand inside microscopic pores, and repeated wetting and drying gradually weaken structures. Despite these challenges, parts of Oricum survived for more than 2,000 years. This raises important questions regarding construction materials. Roman maritime concrete has become one of the most famous engineering mysteries in archaeology. Scientific studies have shown that some Roman harbour structures actually became stronger over time through chemical reactions involving seawater and volcanic minerals. Researchers continue investigating whether similar material technologies were employed at Oricum. If so, local builders may have possessed knowledge of mineral chemistry far beyond what historians once believed. Even today, engineers study Roman concrete in hopes of developing more durable modern construction materials. Perhaps the greatest mystery of all is how much of Oricum remains undiscovered. Geophysical surveys suggest that significant portions of the ancient city remain buried beneath sediment deposits. These hidden areas may contain additional harbour installations, warehouses, ship repair facilities, commercial districts, defensive structures, and hydraulic infrastructure. Every major excavation has revealed new surprises. In many ways, Oricum resembles a sealed archive waiting to be opened. The sediment that obscured the city may also have preserved it. Archaeologists increasingly employ ground-penetrating radar, drone mapping, 3D modelling, sediment analysis, and remote sensing technologies to investigate the site. These tools reveal patterns invisible to earlier generations of researchers. Yet the most important questions remain unanswered. How did ancient engineers select such an effective harbour location? How did they monitor changing coastlines without scientific instruments? How did they maintain navigable waterways for centuries? How did they manage sediment accumulation? How much maritime knowledge disappeared when the city declined? At the northwestern tip of Morocco, where the Atlantic Ocean collides with the Mediterranean Sea, lies one of the world's most unusual cave systems. The Caves of Hercules sit just west of Tangier, overlooking the Strait of Gibraltar, a narrow maritime corridor only about 14 kilometers wide at its closest point. For centuries, travelers, sailors, and historians viewed the caves as little more than a legendary location connected to the myth of Hercules. Modern investigations, however, have revealed something far more intriguing. Archaeologists and geologists studying the site discovered evidence suggesting that large portions of the cave may not be entirely natural. While marine erosion clearly helped create the original chambers, many sections contain geometric surfaces, extraction marks, and unusually regular openings that resemble the remnants of ancient quarrying operations. This discovery transformed the caves from a mythological curiosity into a genuine archaeological mystery. Today, researchers continue to debate a fundamental question: how much of the Caves of Hercules was created by nature, and how much was engineered by ancient humans? The most important mystery surrounding the Caves of Hercules concerns their origin. Geological analysis confirms that the caves formed within sandstone deposits shaped by waves, tides, and coastal erosion over hundreds of thousands of years. Yet many interior chambers display features difficult to explain through natural processes alone. Numerous walls contain flat surfaces, straight edges, and repetitive extraction patterns that resemble quarry marks observed at ancient mining sites throughout the Mediterranean. Researchers have identified areas where blocks appear to have been systematically removed. In some sections, the spacing between cut marks remains remarkably consistent. Such regularity raises an important possibility. Ancient workers may have intentionally enlarged the caves while extracting building stone. This creates a technological puzzle. Ancient quarrying was not simply a matter of breaking rock. Workers needed to understand fracture mechanics, stress distribution, and stone quality. A mistake could trigger collapse, destroy valuable material, or kill workers inside confined spaces. The challenge becomes even greater when the quarry lies directly beside the ocean. Unlike inland extraction sites, the Caves of Hercules were constantly exposed to humidity, saltwater intrusion, and tidal fluctuations. How ancient builders managed these conditions remains unknown. Evidence suggests that stone extraction may have occurred here for centuries, possibly beginning in antiquity. If true, the engineering challenges would have been enormous. Modern quarry operations rely on geological surveys, structural calculations, and heavy machinery. Ancient workers possessed none of these tools, yet they appear to have removed large quantities of stone while preserving the overall stability of the cave system. Comparable mysteries exist elsewhere in the ancient world. At the Hatnab quarries in Egypt, workers transported alabaster blocks weighing several tons across desert terrain. At Aswan, Egyptian engineers extracted granite blocks weighing more than 1,000 tons. At the Maathi quarries on the Greek island of Paros, miners operated deep underground to obtain exceptionally pure marble. The Caves of Hercules present a different challenge altogether. Instead of working in open air, ancient labourers may have operated inside enclosed chambers affected by ocean tides. Researchers still cannot fully explain how these workers illuminated deep sections of the cave. Oil lamps produce smoke that accumulates rapidly in confined spaces. Ventilation systems have not been identified. Likewise, no one knows how quarried stone was transported efficiently through the cave network. The technological knowledge required for such operations appears far greater than commonly assumed. The most famous feature of the caves is the enormous sea-facing opening that remarkably resembles the outline of Africa. Millions of visitors have photographed this formation. Official geological explanations attribute its shape entirely to marine erosion. Waves striking weaknesses in the sandstone gradually enlarged the opening until the present form emerged. Yet, some researchers remain unconvinced. Certain portions of the opening display curves and edges that appear unusually regular. Nearby surfaces contain marks consistent with human modification. While no definitive evidence proves that ancient workers intentionally shaped the opening, neither has anyone conclusively demonstrated that the entire formation is purely natural. This uncertainty has fueled decades of debate. If humans modified the opening, even partially, the implications would be extraordinary. The structure reaches several meters in height and faces one of the busiest maritime passages on Earth. Was it simply the accidental byproduct of quarrying? Or did it serve a larger purpose? The caves occupy one of the most strategically important locations in the ancient world. The Strait of Gibraltar forms the gateway between the Mediterranean and the Atlantic. Every vessel travelling between these regions must pass nearby. For Phoenician, Carthaginian, Roman, and later Islamic sailors, this route represented one of the most critical trade corridors in history. Ancient mariners lacked GPS, radar, and modern charts. Instead, they relied upon visible landmarks. The prominent location of the caves has led some researchers to suggest that the site may have functioned as a navigational reference point. The distinctive opening would have been visible from offshore under favourable conditions. Although direct evidence remains absent, the possibility cannot be dismissed. If the caves served both industrial and navigational purposes, they would represent a sophisticated integration of geology, engineering, and maritime knowledge. Another curious phenomenon involves sound. Visitors frequently report unusual acoustic effects within certain chambers. Scientific measurements indicate that some areas amplify and reflect sound in unexpected ways. Voices can carry farther than anticipated. Echoes persist longer than predicted by simple geometric models. Similar acoustic anomalies have been documented at Newgrange in Ireland, the Hypogeum of Malta, and Chavan de Huantar in Peru. The question is whether these effects are accidental. Natural cave systems often produce echoes, but some chambers within the Caves of Hercules appear unusually effective at concentrating sound. Researchers continue investigating whether quarrying activities inadvertently enhance these properties, or whether specific areas were deliberately modified. No consensus exists. The Atlantic coastline is an exceptionally hostile environment. Salt crystallization, humidity fluctuations, chemical weathering, and wave erosion continuously attack exposed rock. Over long timescales, sandstone typically degrades rapidly, yet significant portions of the Caves of Hercules remain structurally stable. This survival presents an engineering mystery. Some geologists believe ancient quarrying may have unintentionally improved stability by removing weaker sections and leaving stronger structural supports behind. Others argue that workers possessed practical knowledge of rock behaviour acquired through generations of observation. Modern engineers routinely use computer modelling to evaluate stress distribution in rock formations. Ancient builders had only experience. Even so, the caves remained standing after centuries of exposure to one of the most destructive coastal environments imaginable. What do you think? Were the Caves of Hercules shaped entirely by natural forces, or do they preserve evidence of a forgotten ancient engineering project? Let us know your theory in the comments below. In southwestern Albania, roughly 12 kilometers from the Adriatic coast, lies Apollonia, hidden among rolling hills overlooking what was once a navigable river system. It was one of the largest ancient cities ever established in the Western Balkans, founded by Greek colonists from Corinth and Corcyra around 588 BC. Apollonia flourished for nearly 1,000 years before gradually fading into obscurity. Its ruins were never completely forgotten, but systematic archaeological investigations only began during the 19th and 20th centuries. Excavations revealed an enormous urban centre, covering approximately 137 hectares, where monumental temples, administrative buildings, theatres, roads, fortifications, drainage systems, workshops and residential districts emerged from the soil. What archaeologists expected to find was another successful Greek colony, but what they discovered instead was evidence of engineering knowledge that still raises difficult questions today. The greatest mystery of Apollonia is not who built it. The mystery is how ancient engineers managed to create and sustain such a sophisticated city using technologies that supposedly should have imposed severe limitations. The first mystery begins with geography. Ancient cities succeeded or failed largely because of location, as a poor choice could result in flooding, drought, famine, isolation, or military vulnerability. Apollonia appears to have avoided nearly all of these problems. The city was positioned near the Vjosa river system, one of Europe's last major wild rivers, providing access to fresh water, fertile agricultural land, transportation routes, and maritime trade through the nearby Adriatic Sea. Yet the location presents a paradox. River floodplains are notoriously unstable environments, where sediments shift constantly, channels migrate, groundwater levels fluctuate, and seasonal flooding can destroy infrastructure. Modern civil engineers conduct extensive geotechnical surveys before building large urban developments in such environments, but the founders of Apollonia had none of these tools. Nevertheless, archaeological and geological studies indicate that they selected terrain elevated enough to reduce flooding risk while remaining close enough to exploit the river network. The precision of this decision becomes even more remarkable when viewed over centuries rather than decades. Many ancient settlements were abandoned because environmental conditions changed, yet Apollonia thrived for almost a millennium. How did its planners evaluate terrain stability, drainage characteristics, and long-term environmental behavior without modern geological science? No surviving document explains their methods. Today Apollonia stands inland. In antiquity, however, it functioned as a major commercial centre connected to maritime trade. Ancient writers described ships reaching the city through waterways linked to the Adriatic, creating one of the site's most intriguing mysteries: where exactly was the harbour? Geological evidence suggests that river sedimentation gradually altered the landscape. Over centuries, enormous quantities of sediment accumulated, transforming navigable waterways into marshes and eventually dry land. Researchers estimate that river systems can transport millions of tons of sediment annually, and even small changes accumulate dramatically over centuries. Yet, Apollonia remained an important trading centre throughout much of its history. This raises difficult engineering questions. Did ancient planners actively manage waterways? Did they dredge channels? Did they construct embankments or hydraulic structures? Some evidence suggests significant landscape modification, but the full system has never been reconstructed. The disappearance of the harbour infrastructure represents one of the greatest unsolved puzzles of the city, as entire transportation networks appear to have vanished beneath layers of geological change. No large ancient city could survive without reliable water management. Apollonia housed thousands of inhabitants, with some estimates placing the population at more than 10,000 during its peak. while others suggest significantly higher numbers. Such populations require enormous volumes of water. Archaeologists have identified drainage systems, channels, reservoirs, and hydraulic features throughout the site. At first glance, this may seem ordinary, but in reality, water engineering is among the most complex challenges any civilization faces. Modern engineers use mathematical models to calculate flow rates, pressure variations, erosion risks, and drainage capacity, whereas ancient builders relied entirely on observation and experience. Yet many ancient hydraulic systems performed remarkably well. Roman aqueducts maintained gradients as small as a few centimetres per kilometre, and some operated successfully for centuries. Apollonia presents a similar mystery. How did its engineers determine optimal slopes? How did they predict seasonal runoff? How did they prevent sediment accumulation? Even small errors can render drainage networks ineffective. The continued functionality of these systems over generations suggests a level of practical hydrological knowledge that remains poorly understood. Viewed from above, Apollonia reveals evidence of deliberate urban organization. Roads, public spaces, civic structures, and residential districts were not distributed randomly. They formed part of a coherent plan. Creating such a city required accurate surveying. Today, surveyors employ satellites, laser scanners, GPS systems, and digital mapping software. But ancient engineers possessed none of these technologies. Yet Greek urban planners frequently achieved astonishing precision. The famous city of Priene in western Anatolia demonstrates street alignments accurate enough to impress modern architects, and Apollonia appears to belong to this same tradition. Researchers continue to debate the exact methods used. Were measurements based on astronomical observations? Did surveyors employ geometric instruments now lost to history? How were large-scale alignments maintained across expanding districts? No technical manuals survive to answer these questions. The city itself remains the only surviving evidence of the knowledge behind its design. The monumental structures of Apollonia required extraordinary quantities of construction material. Columns, foundations, walls, stairways, temples, and public buildings consumed thousands of tons of stone. Transporting such material was an immense logistical challenge. Even today, moving multi-ton blocks requires cranes, heavy vehicles, and sophisticated planning. Ancient builders relied on human labour, animals, ropes, wooden sledges, and mechanical systems whose details remain uncertain. Experimental archaeologists have demonstrated that surprisingly large stones can be moved using relatively simple technologies. However, scaling these methods to support the construction of an entire city remains difficult. The challenge becomes even greater when considering timelines, as large public projects often had to be completed within political or economic constraints. How were labour forces organised? How were transportation routes maintained? How were materials distributed across construction sites? These questions remain largely unanswered. Perhaps the most overlooked mystery concerns the materials themselves. Many structures at Apollonia survived more than 2,000 years of weathering, earthquakes, biological growth, and environmental change. Their survival reflects more than architecture. It reflects material science. Researchers studying ancient construction materials repeatedly encounter unexpected sophistication. Roman marine concrete remains durable after nearly 2 millennia of exposure to seawater, and recent microscopic analysis has revealed self-healing properties within some Roman concrete mixtures. Ancient builders clearly possessed practical knowledge of chemistry, even if they lacked modern scientific terminology. Apollonia raises similar questions. What aggregate mixtures were used? How were mortars prepared? How were raw materials selected? The recipes have largely disappeared. The structures remain, but the knowledge behind them does not. Some researchers have proposed that certain ancient urban layouts incorporated astronomical considerations. The idea remains controversial. Nevertheless, examples from around the ancient world demonstrate remarkable alignments. Stonehenge aligns with solstitial events. Numerous Egyptian monuments exhibit astronomical orientations, and several Greek sanctuaries appear connected to celestial observations. Could Apollonia contain similar features? Some alignments have attracted scholarly attention, but definitive evidence remains elusive. If astronomical planning played a role, it would imply yet another layer of technical sophistication involving geometry, observation, and long-term record keeping. The question remains open. North of modern Skopje, in present-day North Macedonia, the ruins of Skupi lie scattered across a plateau overlooking the Vardar River valley. Archaeologists first began systematic investigations during the 19th century, but major excavations accelerated throughout the 20th century, revealing the remains of a vast Roman city buried beneath centuries of destruction. What emerged was not merely another provincial settlement. Beneath the soil lay evidence of advanced engineering, sophisticated urban planning, and technological capabilities that continue to puzzle researchers today. Skupi was founded as a Roman colony during the 1st century AD, eventually growing into one of the most important administrative and military centres in the Balkans. At its peak, thousands of residents lived within a carefully organised urban landscape of streets, public buildings, workshops, water systems, and religious structures. Yet the city's greatest mysteries are not found in what survived. They're found in the technological knowledge required to build it. The first mystery begins before construction even started. Modern geological studies show that the Skopje region sits within an active tectonic zone. Throughout history, powerful earthquakes have repeatedly struck the area. The most devastating ancient event occurred in AD 518, when an earthquake reportedly destroyed much of Skupi. This creates an intriguing question. Why would Roman engineers establish one of the largest urban centres in the region on land vulnerable to seismic activity? The Romans were not careless builders. Across the empire, engineers demonstrated remarkable understanding of terrain selection. Cities were typically positioned to maximise access to trade routes, water supplies, agricultural land, and defensible terrain. Skupi certainly satisfied these requirements. It occupied a strategic location controlling important routes connecting the Danube frontier with the Aegean world. Yet the seismic risk remained. Some researchers argue that Roman engineers simply lacked sufficient geological knowledge. Others suggest they recognized the danger, but concluded that the strategic advantages outweighed the risks. However, the possibility remains that Roman builders possessed practical methods for evaluating earthquake hazards that have not survived in written records. The mystery deepens when examining what they actually built. Excavations reveal a city organised according to an extraordinarily precise grid system. The main streets intersected at nearly perfect right angles. Residential districts followed carefully planned alignments. Public buildings were positioned according to a coherent urban design that extended across large areas of the city. Today, such precision is achieved using GPS satellites, laser instruments, and digital mapping technologies. Roman surveyors possessed none of these tools. Instead, they relied on instruments such as the groma, a simple surveying device consisting of vertical and horizontal rods with hanging plumb lines. Historians generally credit the groma for the remarkable accuracy of Roman urban planning. Yet some engineers question whether such instruments alone can fully explain the precision observed in cities like Skupi. Experimental archaeology has demonstrated that achieving consistent right-angle alignments across hundreds of meters requires exceptional skill. Small errors compound rapidly. A deviation of only 1 degree can create significant misalignments across an entire city. Despite these challenges, Roman surveyors repeatedly produced urban layouts of extraordinary accuracy throughout the empire. Similar precision appears at Pompeii, Timgad, Jerash, and dozens of other Roman settlements. The surviving instruments explain part of the achievement. The expertise behind them remains largely unknown. No ancient city could survive without reliable water. The population of Scupi likely numbered in the tens of thousands during its peak centuries. Such a population required enormous quantities of water for drinking, sanitation, industry, agriculture, fountains, baths, and public facilities. Archaeologists have uncovered evidence of pipelines, drainage systems, reservoirs, and hydraulic infrastructure throughout the site. However, portions of the original network remain poorly understood. The challenge facing Roman engineers was immense. Unlike modern cities, they lacked electric pumps. Water movement depended almost entirely upon gravity. Every channel, pipeline, reservoir, and distribution point had to be positioned with extraordinary accuracy. Even a slight error in slope could prevent water from reaching its destination. Modern measurements of Roman aqueducts elsewhere reveal astonishing precision. Some systems maintained gradients of only a few centimeters per 100 meters, while continuing to transport water over distances exceeding 50 kilometers. The famous Aqua Marcia in Rome transported water for approximately 90 kilometers. The Pont du Gard aqueduct in France maintained an average gradient of roughly 34 centimeters per kilometer. If similar principles were employed at Scupi, Roman engineers would have required surveying accuracy approaching levels many people assume impossible for the ancient world. Yet they achieved it repeatedly. How they consistently maintained such precision remains one of the most impressive engineering mysteries of antiquity. The earthquake of AD 518 was catastrophic. Historical accounts describe widespread destruction throughout the region. Many structures collapsed. Large sections of the city were abandoned. Yet surprisingly, numerous foundations, walls, and architectural elements survived. Why? Modern structural engineers studying Roman construction have identified several features that may have improved resilience. Roman builders frequently employed thick masonry walls, flexible mortar compositions, distributed load paths, and robust foundation systems. Recent research into Roman concrete has revealed something even more remarkable. Microscopic analysis conducted by material scientists has shown that some Roman mortars contain lime clasts capable of generating self-healing reactions. When cracks form, water can trigger mineral growth that helps seal damaged areas. The implications are extraordinary. Structures built nearly 2,000 years ago may possess limited self-repair capabilities. Whether similar materials were used throughout Scupi remains uncertain. However, surviving construction suggests Roman builders understood material behavior far better than many earlier historians believed. The earthquake destroyed the city, but it did not erase all evidence of the engineering that created it. One of the most underestimated technological achievements at Scupi involves construction materials. Ancient builders did not possess laboratories. They had no electron microscopes, chemical analyzers, or computerized simulations, yet they consistently produced durable construction materials capable of surviving for centuries. Many walls at Scupi incorporated combinations of stone, brick, and mortar designed to balance strength with flexibility. This combination appears repeatedly across the Roman world. The Pantheon in Rome still stands nearly 2,000 years after its construction. Roman harbours continue to survive exposure to seawater. Bridges, aqueducts, and fortifications remain functional long after many modern structures would require replacement. Researchers studying ancient mortars frequently discover complex mineral compositions resulting from carefully controlled production processes. This raises a difficult question. How did ancient craftsmen determine optimal recipes without modern chemistry? Knowledge was likely transmitted through apprenticeship systems spanning generations. Techniques were refined through observation and experimentation, yet almost none of the technical manuals explaining these methods survive. The structures survived. The science behind them largely vanished. Among the most fascinating discoveries at Scupi are the remains of its Roman theatre. To modern visitors, it appears as a collection of stone foundations. To acoustic engineers, it represents a lost technological achievement. Many Roman theatres demonstrate remarkable sound transmission. Spectators seated dozens of meters away could often hear performers clearly without amplification. Modern researchers have modelled ancient theatres using digital simulations and found that geometry played a crucial role. Curved seating arrangements, reflective surfaces, and carefully designed stage structures created natural amplification effects. The theatre at Epidaurus in Greece remains famous for allowing sounds generated on stage to reach audiences hundreds of feet away. Did Scupi employ similar principles? The surviving remains are incomplete, making reconstruction difficult. Yet evidence suggests Roman architects possessed a sophisticated practical understanding of acoustics centuries before the scientific study of sound formally existed. The mathematics behind their designs may never be fully recovered. High in the rugged Caucasus Mountains of northeastern Georgia, near the border with Chechnya, the stone fortress village of Mutso clings to a steep mountainside at an elevation of nearly 1,900 meters. For centuries, the site remained largely abandoned and isolated from the outside world. Modern archaeological surveys, architectural studies, drone mapping, and restoration projects have revealed that Mutso is far more than a medieval mountain settlement. It is a technological mystery carved directly into one of the most difficult landscapes in Eurasia. Today, visitors see dozens of stone towers, fortified dwellings, defensive walls, shrines, and burial structures seemingly growing out of the mountains themselves. Yet the deeper researchers investigate, the more puzzling Mutso becomes. How did ancient builders construct such a complex settlement on near-vertical terrain? How did these structures survive centuries of earthquakes, landslides, snowstorms, and warfare? And why does the engineering knowledge that created Mutso appear far more sophisticated than many historians once believed? The first mystery appears before examining a single stone. Mutso was built on an extraordinarily steep slope where modern construction would require extensive stabilization, heavy machinery, and advanced logistical planning. Some sections rise directly from rocky cliffs overlooking deep valleys hundreds of meters below. Researchers estimate that thousands of tons of stone were transported and assembled throughout the settlement. Yet, there is no evidence that ancient builders possessed cranes, motorized equipment, or engineered roads capable of supporting large transport systems. The challenge becomes clearer when compared with other mountain fortresses. The famous fortress city of Machu Picchu in Peru sits at approximately 2,430 meters above sea level, while Mutso occupies similarly difficult terrain in the Caucasus. Both sites required builders to solve problems involving transportation, material handling, and slope stabilization without modern technology. Experimental archaeology demonstrates that moving a single one-ton stone block uphill using ropes and human labor can require dozens of workers. Some structures within Mutso contain hundreds of such stones. This raises an unresolved question. How did builders coordinate the transport of massive quantities of material across terrain that remains difficult to access even today? No written engineering manuals survive. No construction records explain the process. The stones remain, but the methods behind their placement remain largely unknown. The Caucasus region experiences significant seismic activity. Over centuries, countless earthquakes have affected northeastern Georgia, yet many of Mutso's towers remain standing for hundreds of years despite constant exposure to seismic stress. This has attracted growing attention from structural engineers. Several towers feature walls that taper slightly inward toward the top. Their bases are wider and heavier than their upper sections. Such geometry lowers the center of gravity and improves stability against lateral forces generated during earthquakes. The same principle appears in ancient structures across the world. Inca builders at Machu Picchu employed trapezoidal doorways and inward-leaning walls. Japanese castle builders developed similar techniques centuries later. Modern earthquake-resistant skyscrapers still rely on managing weight distribution and structural flexibility. What remains unclear is whether Mutso's builders understood these principles through formal engineering knowledge or through generations of practical experimentation. The remarkable survival rate of many structures suggests that their designs were not accidental, yet no documents explain how these mountain engineers acquired such expertise. At first glance, Mutso's architecture appears rough and utilitarian. Closer inspection reveals something very different. Many walls exhibit exceptionally tight stone fitting despite the absence of mortar-rich construction techniques commonly seen elsewhere. In numerous locations, stones interlock with surprising precision. This presents a technological puzzle. Accurate stone construction requires surveying, measurement, shaping, and quality control. Modern masons rely on levels, laser instruments, templates, and standardized tools. The builders of Mutso possessed none of these technologies. Archaeologists studying traditional Caucasian masonry have found evidence that local craftsmen developed highly refined techniques for selecting naturally compatible stones. Rather than forcing stone into predetermined shapes, they identified pieces whose geometry naturally complemented neighbouring blocks. Even so, the level of precision visible in some structures continues to surprise specialists. The mystery is not merely how the stones were shaped, it is how builders maintained consistent construction standards across an entire settlement built over generations. Mutso was never simply a village. It functioned as a defensive fortress integrated into a much larger regional security system. The settlement occupies a position commanding views across multiple valleys and mountain passes. From several towers, observers could monitor approaches from enormous distances. Military historians have compared this arrangement to observation networks used along portions of the Great Wall of China and Byzantine frontier systems. Modern digital terrain analysis has revealed that many watchtower locations maximize visibility while minimizing blind spots. This creates a fascinating question. How did ancient builders determine these optimal positions without aerial maps, satellite imagery, or advanced surveying instruments? The probability of selecting dozens of highly effective defensive locations by chance appears extremely low. Some researchers propose that generations of accumulated local knowledge gradually refine the network. Others suggest that sophisticated surveying techniques may have existed but left little archaeological evidence. Either way, the resulting system demonstrates a level of geographical understanding that continues to impress military planners. Mountain fortresses throughout history faced a common challenge: water. Without reliable access to water, even the strongest fortress could quickly fall during a siege. Mutso's location creates a significant engineering problem. The settlement sits high above valley floors, making daily transport of water difficult and inefficient. Researchers believe inhabitants developed systems involving nearby springs, collection points, storage facilities, and carefully planned access routes. However, the complete hydraulic system remains poorly understood. This uncertainty mirrors mysteries found at other ancient sites. Engineers still debate aspects of water management at Petra in Jordan, Machu Picchu in Peru, and numerous hilltop fortresses throughout Eurasia. The fact that Mutso supported a permanent population for centuries indicates that its inhabitants solved these challenges successfully. The exact methods remain only partially reconstructed. Among Mutso's most unusual features are its crypts and burial structures. Local traditions describe periods of epidemic disease during which infected individuals allegedly isolated themselves inside special burial chambers to protect the broader community. Whether every detail of these stories is historically accurate remains debated. What fascinates researchers is the architecture itself. Several crypts appear carefully positioned to maximize natural airflow. Internal environments show evidence of ventilation patterns that may have influenced preservation conditions. Some specialists have suggested that builders possessed practical knowledge of air circulation and environmental control, even if they lacked scientific terminology to describe it. If true, this would represent another example of sophisticated engineering hidden within seemingly simple stone structures.